Good morning, everyone. I want to kind of give you the 3-minute warning. If you want to grab that last cup of coffee, get yourself settled in, finish the conversation. We'll get started right at 9:30 here. All right, good morning, everyone. It's nice to be here with you and in person and live this year, although we've had some pretty good virtual conferences over the last couple years. Certainly want to welcome you here to the Stranahan and today's meeting. Good morning, I'm Greg LaBarge, and on behalf of Ohio State University, Ohio Sea Grant, and OSU Extension, I want to thank you for attending this year's Understanding Algal Blooms State of the Science Conference. We're glad that so many of you have decided to be here with us in the room, but we also were able to offer a virtual option, and this is being simulcast and people are participating online. First, I want to thank all of you for coming. Our primary goal with this meeting is to bring together a diversity of individuals to hear the science around harmful algal blooms that are impacting Lake Erie. We hope to increase our joint understanding of the science and letting that lead to conversations and a better understanding and solutions to address this wicked problem that we have on Lake Erie. I think we're accomplishing that. As you look around the room, we have registrants from a wide variety of backgrounds and jobs that they're doing today. Registrants are coming from governmental agencies at the city, county, state, and federal level. We have 13 academic institutions represented within the registrants for this meeting. We have agricultural groups, business, industry, consulting firms, NGOs, and we have some practitioners in the room who are actually working with farmers on conservation implementation in their farming situation. So we greatly appreciate all those folks being there, and it's the joint efforts of all of us that are going to lead to these solutions. We do want to call out our elected officials who provide the funding for a lot of the programs that we're going to talk about today, the research that we talk about today. And if we could, any of the elected officials or their representatives, if you could stand so that we can know where you're at and talk to you later today. Back in the back. Great. We are also encouraged by the number of students that are here today, both graduate, undergraduates. We greatly appreciate them participating in this conference and our future leaders that will be continuing with this issue, because unfortunately, I don't believe it's a short-term issue. At least for me, I've got another couple years in this industry and working with it before thinking about retirement. As we search for win-win solutions to improve our water quality while increasing ag production, it is vital to have all these different folks in the room sharing their perspectives, sharing how practices and programs and different opportunities impact them, so that we can have a joint understanding of how to best address what we have here as far as the issue on Lake Erie. And it is so great to see all of you in this room and your interest in this topic. Next I want to recognize some organizations and individuals who have been key to having this conference be pulled off. First, we want to thank our sponsors, and they're listed there on the screen. We greatly appreciate their financial contributions, which has allowed us to overall keep our registration costs low. The students that are participating have a reduced rate, $10, and their contribution is helping offset that. And the virtual option, while we're glad to have that, it also has an expense to it that we need to cover. So we really want to thank these sponsors. The MOME contributors to this are the Joyce Foundation, the Lake Erie Foundation, Great Lakes Center for Freshwater and Human Health Community Engagement Corps, Fred A. and Barbara M. Erb Family Foundation. The Auglaize sponsors are Ohio State University Extension Strategic Innovation State Support, the Ohio State College of Food, Agriculture, and Environmental Sciences, and the National Wildlife Federation. Ohio Farm Bureau Federation, Ohio Soybean Council, Ohio Corn and Wheat, Ohio Dairy Producers Association, American Dairy Association Mideast, the Ohio Pork Producers Council, Limnotech, the Nature Conservancy, and the Great Lakes Commission. A wide variety of folks helping us pull this conference off, and we greatly appreciate it. And let's give them a round of applause. I also want to thank my co-chairs for this meeting, Kristen Fussell and Chris Winslow from Ohio Sea Grant, Kevin King with USDA ARS, and Jay Martin with our Ag Engineering Group down at OSU. Most important, there's always somebody that does all the work, and I want to recognize them. That is Shalise Simmons with OSU Extension, and Aaron Monaco with Ohio Sea Grant, who does the heavy lifting behind this program. They're managing the registration, vendors, budget, getting those name tags out, and working with the venue here with the meeting arrangements. So let's give them a round of applause too. And last but not least, he's going to keep us on task today and give us a good visual look at everything that's going on, and that's Joe with our AV group, and he helped provide some good tunes to get us started out today. Next thing on the list is just a few of those logistic reminders for the day. We do want to be conscious that COVID still is a part of our world, and this disease has impacted individuals and their households differently. When you walked in, you were given the opportunity to fill out a name tag and identify how you'd like to interact today based off the color of the dot that you put on your name tag. I guess I push this forward. We've got the code there, just how you want to interact with folks today as you interact with them during the conference. Today's agenda has 2 sessions with a lunch in between. We did simplify and shorten this year's program because of being an in-person event for the first time and getting back to that. One missing element that we have this year is we used to have some student posters along the left-hand side as I look at it, right hand as you're looking at the screen, and we hope to bring that back in a future year, but that is one element that we don't have this year. There are no planned breaks during the sessions today, so please feel free to go back to the beverages, the restrooms. I hope you saw as you came in back behind the screen and back past the registration desk. Important to us as a planning committee is after the meeting you will receive an email with a post-conference survey link. Your input is vital to us. Helps us keep this conference relevant to meet a diversity of needs, which with this wide diversity of folks in the room, we certainly have those different needs that we want to try and fulfill with this conference. Please let us know what you think about today's meeting and share any ideals for future meetings with that survey. I want to invite Jay Martin to come up, and he's going to share a statement with us, and then we'll move forward.
Good morning, everyone. It is great to see everybody in person after being virtual for a few years. I am Jay Martin from the Department of Food, Agricultural, and Biological Engineering and the Ohio State University Sustainability Institute. Because Lake Erie and the surrounding lands were and are integral parts of indigenous communities, I will now proceed with a land acknowledgement statement. I would like to acknowledge the land and waters of Western Lake Erie Basin are the ancestral and contemporary territory of the Anishinaabe Three Fires Confederacy of Ojibwa, Ottawa, Potawatomi, and the Erie, Haudenosaunee, Mississauga, Kaskaskia, Miamia, Peoria, Kickapoo, Fox, Caldwell, and other indigenous peoples. I want to honor the resiliency of these tribal nations and recognize the historical context that has and continues to affect the indigenous peoples of this land. Acknowledging this history does not change the past, but a thorough understanding of its ongoing, unjust consequences can empower us to create a more just future. Thank you.
Thank you, Jay. I would not have been able to give justice to all the tribal names, so I'm glad that we had you come up and share that with us. My folks for this meeting, anything that I'm missing, because I think we're ready to jump into speakers. Good to go, Chris. All right, we're going to jump into the session and get started with our first speaker. Chad Penn from USDA ARS, National Soil Erosion Research Laboratory located at Purdue University, is going to be our keynote kickoff speaker today. Chad has a BS in Soil Scientist from Penn State University, an MS in Environmental Soil Science from the University of Delaware, and a PhD in Soil Chemistry from Virginia Tech. His current research is focused on nutrient transport mechanisms, improving plant nutrient recommendations, thermodynamics of surface reactions, design and construction of phosphorus removal structures, and animal waste management. And I know Chad most for his work in phosphorus removal structures, and we certainly have the expert on that here to share this first topic with us, that is honing in on sources of dissolved P, targeting legacy soils with phosphorus removal structures.
Thank you, Greg. Okay. All right, good. I'm glad you're taking care of it because I'm gonna put my stopwatch on pause here because. I guess it's only going to work if I look at it, right? Make sure I look at that thing. So we're going to start out, before we get to peer removal structures, we're going to talk about dissolved phosphorus and its nature, particularly the dynamic between soil phosphorus and the solution pool. And the reason why we're going to focus on the dissolved pool is because, well, quite frankly, I don't think I need to explain to this audience about the dissolved pool, why it's so important with regard to surface water eutrophication. But another thing to keep in mind is that the dissolved phase of phosphorus is the pool that plants what they truly uptake. And it's extremely dynamic, all right? So it's much more difficult to control or manipulate compared to your solid bound, your sediment bound particulate phosphorus. And again, the reason for this is because dissolved P is so much more dynamic. Part of that reason is because solubility varies with chemical conditions, but it's beyond that. It's more than just chemical solubility. Its behavior is also a function of its physical location, hydrology, and also kinetics. I'd like to touch on some of those things before we get to peer removal structures. So the nature, the dynamic between the solid phase and the solution phase is that of a chemical equilibrium. It's based on thermodynamics, and for phosphorus, it is dominated by abiotic processes, totally different from nitrogen. Nitrogen cycling is dominated by biological processes, but if we wanted to separate it generically, we could take the solid phase soil-bound pool and put it into three main mechanisms in which it's bound. You've got precipitated phosphorus minerals that can precipitate into the solid phase, dissolve back into solution. You've got phosphorus that's bound by anion exchange mechanisms, again, adsorption, desorption in the solution, and also ligand exchange mechanisms. Either way, all of these means in which it's bound to the soil, it can move into solution, back into the solid phase, and once it's in solution, now it can be taken up by a plant, or it can be lost as runoff or leaching. So dissolved phosphorus is very dynamic. As you have that equilibrium develops between the solid phase and the solution phase, a lot of things can happen. And so as a result of this, what we observe is that dissolved phosphorus concentrations lost in flow is very flashy, totally different from nitrogen. So what you see here, this is from data from Kevin King and Laura Johnson several years ago, but it shows a hydrograph with dissolved P concentrations, not loads, mind you. These are true concentrations plotted with the hydrograph. And what you see, and this is very common, it's very flashy. The dissolved P concentrations basically move with the hydrograph. Greater concentrations, not just loads, are lost with your higher flows. This is totally opposite of nitrogen. Nitrogen is a steady loss from the moment it's applied. Even if you don't apply phosphorus fertilizer, you still observe this pattern. So why is this? Why does phosphorus behave so radically different from nitrogen and so flashy like this? It's because, consider the source, soils. Soils are very well buffered in phosphorus, unlike nitrogen. Why? Again, it goes back to that dynamic between the solid phase and the solution phase. So at this scale here, on the left, you have phosphorus lost at the edge of field, all the way up to the right at the Maumee. The pattern is the same. So ultimately, it's apparent that hydrology is partly controlling desorption from the soil. It doesn't control just the loads, not just a function of volume because of loads. It controls the concentration as well. The problem, this is fine, but the issue with this is that our current models do not capture this variability, all right? So our current models simply predict dissolved P concentrations in solution empirically as a function of soil test P levels. So you have some sort of relationship such as this, where you have Mehlich 3 or Bray or whatever, correlated to concentration in tile, drain, or surface flow, or even just concentration shaking it with water in a tube, either way. And based on that, they use that relationship to estimate the concentration in solution. So for example, if your soil test peak concentration was around 100 milligrams per kilogram, you'd expect around 0.2 milligrams per liter dissolved P in solution. And using that approach, well then, it would never it's impossible for it to capture that variability. It simply predicts a static concentration of dissolved P in flow, regardless of that change in the hydrograph. It is not able to capture the dynamic nature of phosphorus. So it's a huge shortcoming with our models. Why are these models not able to capture this? All right, well, this thing is awfully touchy. Okay. Maybe I should aim it right. Like I said before, it's the movement between your solid phase pool and your solution pool, your dissolved pool, it's a thermodynamic process, equilibrium-based process. However, it requires, it's not just an equilibrium-based process, it requires time. It's a kinetic process. And fortunately, the same properties that control the equilibrium between the solid phase and the solution phase are also the same properties that control how fast phosphorus is able to desorb. I could summarize a very large portion of this presentation by simply stating that it takes time and water to desorb phosphorus, which is just another way of saying thermodynamic equilibrium and kinetics, time and water. Okay. So it's not just the speed of the chemical reaction that matters. There's a lot of things that need to be put in place physically before desorption and adsorption as well, for that matter, can occur. There's diffusion. Water needs to move with the phosphorus, dissolved phosphorus, into its proper place. So you've got bulk diffusion through the bulk solution. You've got film diffusion at the surface of particles, and then you have intraparticle diffusion as well. Only then can the chemical process of desorption be fully realized. So it's not just a chemical process, it's a physiochemical process. And this is partly what we're missing with our modeling efforts. So, like I said, P-desorption, it's not a purely chemical process. The overall objective to this body of research, and it's a body of research, it's not just a single study, we want to better understand how does the physical interaction of water impact the net measured desorption. You saw the result of that with that hydrograph. As that hydrograph goes up and down, your concentrations vary dramatically. It's not static as our models would estimate. Specifically, we want to know how does that physical interaction between soil and water have an impact on the quantity of phosphorus desorbed and the rate in which it's desorbed. So we started out by thoroughly studying a high P soil to understand these processes, a whole series of different batch and flow through tests. I can't get into the details of that here. That's published in a previous study here in the journal Soil Processes, if you'd like to take a look at that. But I'm going to share with you a few things that we learned from that. So there's two physiochemical processes or aspects that are the most important when we're talking about the kinetics of phosphorus desorption and that dynamic between the solid phase and the solution phase. One is reaction order, and the second one is diffusion. Reaction order is what describes how concentration impacts desorption rate. So both of these, reaction order and diffusion, are going to have an impact on desorption quantity, rate, and the buffering of the soil. So first of all, one thing we learned is that phosphorus desorption from soil is a first order kinetic process. That means it's dependent on concentration. In other words, being first order, the larger the discrepancy between your solid phase soil pool and your solution dissolved phase, the faster it will desorb. So dilution and your solid dissolution ratio is going to have a dramatic effect on the rate. The more you dilute it, the faster it can desorb. One method that we used a lot in studying this is a flow-through technique. It's a bit, essentially this is like a thin film disc chromatography, where we control the flow rate and the contact time of the solution through the soil. And we mostly tested a fast and slow flow rate to represent flow rates under similar to preferential flow and matrix flow. All right, one thing I can tell you for sure is this: flow rate makes a huge difference. I think you already knew that, though, based on the first few slides. But in general, fast flow rates produce lower concentrations in solution compared to slow flow rates. A huge difference. But the higher flow rates desorb phosphorus much faster than the slow flow rate. So in this case, time on the x-axis. The slope of that curve is the desorption rate. And that slope is going to get lesser and lesser eventually until the soil source, the soil pool, is exhausted. However, the slow flow rate, while it desorbs phosphorus more slowly, it desorbs a greater quantity of phosphorus at any given volume compared to the fast flow rate. I mentioned first order kinetics earlier. Get a little more detail on that. I mentioned that it was first order. In fact, desorption of phosphorus from soils, it's a two-stage first order process. So initially you get you have an initial rapid desorption that occurs, first order, and then you have a transition phase where you have a secondary gradual release of phosphorus that is limited by the less labile pool. The initial desorption that's faster is more supported by the more highly labile pool. So again, it's a two-stage process with regard to kinetics, at least. Diffusion is the other main process that really dictates kinetics of phosphorus desorption. One thing we did was that we conducted these interruption tests during our flow through, where we monitored we measured the desorption rate with time as we continued the desorption process through the flow cells. And then we would interrupt the flow test, we would stop all flow through it and allow the soil to re-equilibrate for 24 to 48 hours and restart it again. And what we found was that your desorption rate never picked up where it left off. In fact, it almost always started at a desorption rate similar to what it was initially. This is a huge sign that the system is limited by the process of diffusion. All right? And this is what makes phosphorus radically different from nitrogen. Essentially, this diffusion is how soils are buffered. Diffusion is buffering. And the other thing to keep in mind from this is that while soils are limited in phosphorus desorption, I should say, is limited by diffusion, it's more limited by diffusion with fast flow rates, or less limited by diffusion at slow flow rates. So what do I mean by that? So this diffusion is how soils are buffered. If you can imagine water moving through a soil, you have bulk flow between aggregates, and it is this advection process is what removes phosphorus from your more labile pools. But it's the phosphorus located within aggregates and between particles, as indicated by the red arrows here, is where diffusion occurs. And that diffusion is very sensitive to flow rate. A slow flow rate is going to allow diffusion to occur more easily. A fast flow rate is not going to allow diffusion to occur very readily. And this was very apparent with our flow test conducted at different rates. Okay, another attempt to illustrate this. If you can imagine, I'll contrast the slow flow rate to the fast flow rate. So you've got your labile soil phosphorus pool that's feeding your solution pool. It's in equilibrium with it. And as you strip phosphorus from that, your less labile pool is also in equilibrium with the labile pool. All right, so as you strip that pool, your less labile pool replenishes it, okay? And eventually, your less labile pool is not going to be able to keep up. That process, if you recall, is controlled by diffusion, which is fairly slow. So it's going to keep desorbing, refilling that labile pool, and as the labile pool feeds the solution until it can no longer keep up. So the less labile pool, it keeps up for a while, but compared to a fast flow rate, and with fast flow rate, we'll call first order kinetics, you were depleting your labile pool very, very fast. But at the same time, with that fast flow rate, your diffusion is much less effective. So now your less labile pool is not able to keep up. It's not able to replenish that labile pool very fast at all, because you have ultimately less effective diffusion. So what do we know? What do we learn from this? Ultimately, phosphorus desorption, quantity and rate are a function of both time and water. Both of these factors are captured by the variable flow rate, and it's a physiochemical process. It's not purely chemical. Phosphorus desorption, it's dictated by a two-stage first-order kinetics. You have an initial rapid phase followed by a secondary gradual release. So dilution has a big impact on it. The more you dilute it, the faster it can desorb. Also, desorption and buffering is limited by the diffusion process. Ultimately, your slow flow rates is going to desorb more phosphorus than your fast flow, but it does it at a slower rate. So how are soil properties going to affect how flow rate influences phosphorus desorption and the degree of desorption rather, and the speed of it, the kinetics? So we repeated this essentially for over 30 soils. Some of them are high P soils. In this case, I'm going to show you mostly the high P soils from Ohio, collected from various studies from Jay and from Kevin, and some of them are from around the United States. And as you'd expect, malic 3, as your soils increase in malic 3 phosphorus, you desorb a greater amount. The other thing was it confirmed that the slow flow rate always desorbs more phosphorus than the fast flow rate, always. On average, your slow flow rate would desorb twice as much more phosphorus than the fast flow rate. So what was interesting, though, was that the difference in the phosphorus released between the slow rate and the fast rate increases as the soil malic 3 content increases. There's a little bit of a pause in these animations here, and then when I skip it, it goes 2 of them. Yep. All right. Similar results for desorption rate. Last one was the quantity, but also the rate. This was interesting. And it makes sense. Because it's dictated by first-order kinetics, the more malic 3, the higher soil P levels you have, the faster it can desorb it as well. Again, that's first-order kinetics. But again, one thing that was interesting was that the difference in the desorption rate between the initial faster rate and the secondary gradual phase became larger and larger as malic 3P increased. Why this thing? Okay, so another thing that I can't get all the details of this study, but malic 3 was obviously a big factor, as you would expect, but also clay content came out to be a really, really important soil property that dictated how flow rate would control desorption rate. So changes in flow rate have a more dramatic effect on clay soils than sandy soils. Changing flow rate on sandy soils didn't have nearly as much of an effect as clay soils. Why? Clay soils, because they are much more, they have much more physical restrictions than sand, are more diffusion limited. And so when you slow down the flow rate through a clay soil, you're able to more fully realize its potential in phosphorus desorption. So flow rate has a dramatic effect on P desorption quantity and rate from clay soils, not nearly as much from sandy soils. All right, so who cares? Well, understanding this, the nature of phosphorus behavior, is going to help us to improve transport models, create better and improve phosphorus fertility recommendations, especially if you take a mechanistic approach, and better target best management practices. summarize this by saying that all of these things are impacted by soil-water, water-soil interactions. Give some examples of that. Mark Williams, our hydrologist, Mark studies how water moves into a tile drain. And I'll say, there's probably, in my opinion, there's probably no one in the Midwest who understands how water moves into a tile drain better than Mark Williams. It's a very complex process. Use isotopes and other techniques to do that. But basically, Mark is able to separate the water coming out of a tile drain into whether it's dominated by precipitation, soil water, or groundwater. And let's give some kind of summary points of things that he's learned here. This one's no surprise. Essentially, water sources, when the water source comes from near the surface, you get greater dissolved P concentrations. Okay, another application of this, or I should say implication of this soil-water interaction, how it affects dissolved P loss, is that your discharge and the water sources will vary with your antecedent moisture conditions, which have an impact on dissolved P concentrations. Specifically, he summarized it this way. When you have wet conditions, in other words, your water table is above the tile depth, you tend to get large flows that are proportional to the amount of precipitation. The water then coming out of your tile is dominated by groundwater. And so you tend to get lower, but more consistent, less variable dissolved P concentrations. Contrast that to when you have dry conditions, your water table is below the tile, and you tend to get small or negligible flows, and the water coming out of the tile is more dominated with precipitation, with water that came from the event. And you get greater dissolved P concentrations, but they're much more variable. Another implication of this is from some of Jay's work on a variety of high P testing soils around Ohio. Here we have phosphorus loading, both total and dissolved, and from sites B through L, which are in order of soil test P content, Malic 3, from 550 all the way down to 75 milligrams per kilogram. So you would expect your greatest loading to be on the left, and your bars should get smaller as you go to the right, which is true generally, but you notice there are lots of inconsistencies here, right? You have high P soils that aren't producing a lot of flow in runoff, and then you have vice versa. So it's clear. Soil test phosphorus is not the only factor controlling phosphorus loss. These soil-water interactions make a big difference. You can have high testing soils that still, depending on that soil-water interaction and other factors, may not exceed the water quality thresholds as shown in the dashed green line there. Okay, so, all right. So what do you do when you end up developing in the situation where you have a legacy phosphorus soil? Well, it's a big problem because it's a long-term problem. Your soils get built up, high levels of phosphorus, they're gonna stay high for a long time. Obviously, the root of the problem is to cease phosphorus applications and start to draw down that soil. All right, but several studies, I'm showing just one here from Eastern Shore of Maryland, and it varies with soil type, but through that process, let's say your soils are built up with Malic 3 phosphorus from 200 to 300 milligrams per kilogram, it's going to take 20 to 30 years to drop that soil test P level down to agronomically optimum levels. So during that time of drawdown, every time you get a flow event, you're leaking out some dissolved phosphorus. So because of that, the phosphorus removal structure was developed as kind of a Band-Aid, if you may, to trap that phosphorus during that, you want to call it a remediation process. So in theory, what are P removal structures? It's nothing more than a large landscape scale filter. You have a filter media that has affinity for dissolved phosphorus. We call that media a PSM, phosphorus sorption material, and you channel flow through that media and retain that media so that it is not lost in flow. There's three necessary components to a phosphorus removal structure. You can build them in all kinds of situations. They can look a lot of different ways, but they all contain these three characteristics. They must have an effective PSM in sufficient quantity. You have to have enough of that PSM to handle the load, a sufficient percentage of the load, lifetime, this thing, and it has to be able to handle a sufficient flow rate at a sufficient contact time. All right, so recall that the majority of your dissolved phosphorus is lost with your biggest events. So you need to be able to design your structures to handle high flow rates and be in contact with them for a sufficient amount of time. They also need to be designed to retain the PSM and then replace them when necessary. So if you have all three of those things, it's a P removal structure, and as a result, we built all different types in all different situations, and they're quite diverse in their appearance. I'll share some of those with you today. The materials can also vary as well, although they are definitely not all created equally. Some are industrial byproducts, some are manufactured. Manufactured ones tend to be extremely efficient, but almost all of them are cost prohibitive. I'll tell you that right now. Some of them are, some of the ones that are borderline, some of them that are okay, we'll test those ones in the field. The other ones, we can't even afford to buy enough of them to test them in a single large unit. So, the physical components of the unit, there's several components. You have to have some sort of a distribution system for the water, for the untreated water to flow into it. Usually we use perforated pipe. It doesn't have to be. You obviously have to have a filter bed of the media, the PSMs, and then you need some sort of a drainage or collection pipes for removing that treated water from the structure so new untreated water can move in. This is just a generic representation of it, but they don't have to look exactly like this. You've got this, in this case, we're showing one for tile drainage. Doesn't have to be for tile drainage, but oftentimes we have bypasses built into them to take overflow in case it ever clogs or can't handle the flow. Distribute the water coming in, and then the collection pipe down below. This is cost shared under the NRCS Standard 782 in states that have adopted it. I believe it is in Ohio, Indiana, Pennsylvania, Maryland, Delaware, Wisconsin, New York, Vermont, Oklahoma, not sure, maybe Texas. There may be some others, but it is in the EQIP program. We have developed a software that can be used to help in design. It's kind of allows non-engineers to do a design. That's the goal. I can't get into detail. I give a whole presentation on just the software alone, but essentially you have to collect certain inputs about the site hydrology, dissolved P concentrations, your target removal goals of lifetime, how much phosphorus you remove, obviously some sort of a characterization of your P sorption materials, and it spits out for you design specs for your site, for your PSM material, for your removal goals. This is what it looks like. Easiest way to find it is to simply just Google P-trap phosphorus. And there's lots of help buttons all over it, information buttons you can click on to learn more about the inputs, what they are, and how to obtain them. A little bit more on this later. This will be included in a series of training modules that'll be coming out in January. Okay, so before I get into a kind of a survey of some different types of structures we built, I do want to say this. If a site is worth treating, then it's going to require a large mass of P sorption materials. Why? It's because you need to be able to handle a high flow rate. All right, I mentioned that earlier. That's when most of your dissolved P is transported. You need to be able to handle a high flow rate, so it's going to require a large mass, and you need to have a sufficient contact time. If you need to do both of those things at the same time, that translates to a large mass of media. Also, if you want it to have a useful lifetime, it's going to require a large mass of media, not just some cartridge or little filter that you plug in at the end of a tile drain, okay? It sounds real nice. In theory, you got something modular you can stick there and plug in and take out, and the commercial entities really like this idea. But the problem is it only works in limited situations. In fact, so limited that it's not even worth using them, okay? And the reason why is because they contain such a small amount of media, they have a extremely poor flow rate or a very low contact time. So in general, like I said, I wish I could sit up here and tell you it was that easy. If it was this easy, we wouldn't have a problem. I'll put it to you that way. Similar with filter socks. Filter socks, sounds nice in theory, it doesn't work. It doesn't work for the same reasons. They have a limited mass, and so you also have very poor contact between the water and the filter media, and poor contact time. So filter socks, don't waste your time on those. So currently, the current state of the technology is that it's effective, but it can always be improved. And as a researcher, my goal is to decreasing cost and improving the efficiency. I'm going to give you a brief survey of some different styles and structures we've built over the years. This is a confined bed structure. It treats surface water. This one was located on a poultry farm in eastern Oklahoma. It contained about 40 tons of a aluminum-treated steel slag. I don't know why it keeps doing that. And it handled about 1,000 gallons per minute of flow. This cost about $5,000. You have a perforated pipe up on the upslope side that distributes the water evenly through the bed. It drains down through into another series of drainage pipe that carries the clean water out. This removed around 30% of the 2-year dissolved P load. It was okay. So that's what I call a confined bed. Also, you can do this in ditches. We've built a lot of ditch filters, especially on the eastern shore of Maryland, just similar to the confined bed, except you have the ditch itself to retain the media. And so the advantage of this is that it allows a large amount of material to be used. You have to be very careful, though, because ditches are there for a reason, all right? And so there are other variations of this. I don't have time to go into detail. Some ditch bypasses. So you have to be very careful about building those. I wish I could say more on that right now, but we don't have time. They tend to be pretty low cost. We built, 10 to 15 of these in the eastern shore of Maryland, and the media that we used wasn't that great, so they ended up removing, over 2 years, they removed about 40%. It was okay. We can do much better than that now. Another option is a blind inlet. So blind inlets, I should say a modified blind inlet. A blind inlet as is not necessarily a P removal structure. Refresh your memory in case you don't know what a blind inlet is. Essentially, a blind inlet is when you replace those orange Hickenbottom risers that are located in drainage depressions with basically a gravel or a sand bed that has a layer of perforated pipe underneath it that acts to filter out all the sediment. And they're very good at reducing sediment, but they just use regular sand or gravel, and it doesn't do anything for dissolved phosphorus. However, if you amend that media with P sorption material, it becomes not only a blind inlet, but a P removal structure. And we've done that using steel slag. In this case, for over 3 years, the last year of a 3-year run, we removed 46% of the dissolved P load, and it also removed dicamba, glyphosate, some other things as well. Last summer, we changed this filter from this blind inlet media from slag to gravel metal shavings mixture, and it will remove a lot more phosphorus compared to that slag, and it's also pretty cheap. We're working on an economics paper to put out, or to be released soon, and from that I can say blind inlets are the most economical opportunity for a P removal structure. This was cheap. This is only about $3,000, and in this situation it'll remove phosphorus for probably 20 years sufficiently. This is what the metal shavings, this is 8% gravel mixed with metal shavings mixture. More on that later. Similar, you have bioretention cells in urban areas. They're nothing more than an urban blind inlet, but they can be modified as well to do the same thing. We built a lot of these in eastern Oklahoma, mixing sand with fly ash. Tile drains is where a lot of people would like to apply these in the Midwest, and essentially it's like having imagine your surface bed buried beneath the surface where you plumb your tile drain directly into it, and you can design those so that the water flows through the PSM media from the top down or from the bottom up, and you can build these a lot of different ways, as beds, in tanks. Here's one being built in I should say Northwest Ohio, your layers of perforated pipe as the drainage on the upper left, and on the lower right, we have the inflow distribution pipe. So they can be beds that are buried. They can also be in tanks. This is an in-tank structure. This one was constructed by Kevin King's group in north of Columbus. In this particular unit, we used a couple tons of activated alumina to filter the media. It was designed to remove 40% of the 10-year load. It cost about $12,000. Speaking of tanks, Jay Martin's group also built a couple structures they're also monitoring as well. Kevin monitors his. Additionally, he has a couple tanks, one with the gravel metal shavings mixture, another one with the material manufactured media called Alcan. It's an iron-coated activated alumina. They're both removing around 50% of the dissolved phosphorus after about 2 years. Metal shavings, I mentioned that a couple times, is probably the most economical media. It's an 8% mixture of shredded metal shavings with gravel, a good clean wash pea gravel. And those metal shavings are steel. As they oxidize and rust, they produce iron oxide, which has a very high affinity for dissolved phosphorus. We've built some beds with these metal shavings mixtures, buried beds not in tanks. Kevin's built some in tanks. I have some in tanks. Jay has some in a tank. We did one as a bed, a very large 50-ton unit up in Michigan. This is on a swine farm near Holland. It's a top-down drainage system. Here you can see the lower drainage, the bottom drainage that collects the treated water. And here they're filling it with the PSM mixture. And you can see the distribution pipe there located on top. This was then covered with a tarp before burial. We used a flow control structure also as a bypass. This one cost about $7,000 to build and was constructed by the Levy Plant Tough Corporation. A really ideal setting for pre-removal structures works really, really nice hand in hand with your treatment wetlands or wascobs. So if you can imagine, you're retaining the water in the landscape with these wetlands, dropping out the sediment, and then slowly petering out the water into a pea removal structure. All right, and this is something our friends in Wisconsin are starting to do. Great advantages. It's a perfect match. The wetland drops out the sediment, and it removes your particulate pea. Problem is wetlands don't do really hardly anything at all for dissolved pea. So tacking a pea removal structure on the back end, well, it prevents clogging of the pea removal structure, and also it provides a hydraulic buffer for that surface water. In other words, you won't need to design a pea removal structure that can treat 2,000 gallons per minute because you can store it and slowly release it from that retained water. It's similar to what water table control structures can do for tile drainage in this case. All right, last couple of things I want to say here. If you don't remember anything from this presentation, remember this. Do not use normal slag for treating subsurface drainage water, tile drainage, unless you plan to replace the media annually. Because I promise you, it will clog up and it will also be burned out prematurely. In fact, and I've learned this the hard way several times. I can't get into the chemistry of how it works. You just got to trust me on this one right now. As a matter of fact, don't use any calcium-based pea sorption material for subsurface drainage. Slag and the other calcium-based materials work great for surface water and blind inlets. It works great for silage runoff, not for subsurface water, not for tile drains. We have a mobile pea removal structure demo unit that should be constructed by the end of this month. So hopefully, probably, I don't know, I would guess in the spring or summer, we can take it out and do demonstrations and show people how they work. If they're not able to travel to a pea removal structure, I guess we can bring it to them. There's a series of training modules that are to be released in January to train people and also become certified in the design and construction of pea removal structures. 2 series, one for conservationists, another one for engineers. And yeah, look for those. They'll also contain some guidance on how to use the software as well. All right. All right, I didn't leave much time for questions at all. I apologize for that, but I have, my email is My email's up here. Twitter handle, sometimes we'll throw some things out when we're getting ready to build structures if people want to come and watch. But if help on that or questions, please feel free to contact me. Thank you.
Since we have Chad here, we are going to take time for a couple questions. We're going to do questions via the microphones if you have anything you'd like to ask Chad here based off of his presentation. And Chad, I guess the one question that I have, talking about all the chemistry of phosphorus, one thing that we talk a lot about is if we could just control DRP separately, then we would have the solution to the problem. But reality is, because of the continuum, is that even possible? Are there any practices other than the P removal structure or adjusting soil test levels that are going to work for DRP control?
Yeah, decreasing the solubility, you're right, Greg. Decreasing the solubility of phosphorus in soils is a sure bet, and the easiest way to do it, the most direct way to do that is to draw it down through crops. We can also decrease the solubility through pH adjustments, things like that. But other than changing the solubility, well, we have P removal structures to filter it. The other thing you can do is reduce the volume of water leaving your fields. That's a big one right there. Now, obviously, you can't keep all of it. If we have watershed, watersheds exist for a reason, right? It has to go somewhere. But if we can reduce the amount that leaves the site, it will help. Also, promoting infiltration, going down into the subsoil. Your subsoil is like a giant natural P removal structure. A lot of times, people, subsurface drainage gets a bad rap, but I'll put it to you this way. If I have the choice of that water going down or off in surface runoff, I want it to go down all day long, because you want that water, that high concentration at the surface, that water to interact with the low P subsoil and absorb it. It's like I said, it's like a giant P removal structure, as opposed to have it running off. Much higher concentrations in surface runoff than we have in subsurface flow.
And question?
Yes, thank you. Chad, really enjoyed your presentation, and in the context of what you've been able to learn in terms of water interacting with soils and contributing to dissolved reactive phosphorus loss, how do you think that would potentially scale up when you look at implementing best management practices across a watershed? Is it more valuable to try to address agricultural floodplains? Is it more valuable to address upland areas that have high soil test phosphorus and a high clay content? Where do you think it's best for us to use limited resources to put best management practices on the landscape in the context of how watershed works, rivers work, and how hydrology moves?
Great question. I put this in the category of what do they call it? Precision conservation, target conservation, which obviously we have limited dollars as you alluded to, and so put the money into high testing soils all the time. Your high P soils, and that's the thing. We don't necessarily know where all the high P soils are. They're your biggest sources. Those are low-hanging fruit. That is definitely where I would put the resources into. With regard to drawing the soils down, P removal structures. Another thing I should have mentioned, P removal structures, these are only intended for your hot spots, okay? This is not a best management practice that you just throw on any old tile drain. It's intended only where you have high dissolved P concentrations, at least around 0.15, 0.2 milligrams per liter of dissolved P in flow. So yes, target those high P soils. How to find them? That's a bit more difficult, because the producers that are jumping up and down volunteering to do a lot of these conservation efforts and to build P removal structures, they often don't have a problem with dissolved P. So it's a bit of a catch-22.
Okay. Chad, are you going to be here the rest of the day, or when are you leaving?
I'll probably leave after lunch, so we can catch up at lunchtime.
Yes, so Chris, I have 2 online questions, and I'll get you after lunch, and we'll just type those in, so you're good to go. We'll
All right.
Thanks, Chad.
Let's thank Chad. Great. Our next presentation, our presenter is Jordan Haywisher. Jordan is the Director of Water Quality and Research at Ohio Farm Bureau Federation. Jordan has a BS in Turf Grass Science from The Ohio State University and also an MS in Natural Resources and Environmental Sciences from the University of Illinois Champaign. Jordan spent 8 years with Scott's Miracle-Gro in their research area and has for the past 7 years been leading with Ohio Farm Bureau their Blanchard River Demonstration Farms Network, which is a partnership with the USDA ARS. Another hat that Jordan wears is working with the Ohio Agricultural Conservation Initiative and OACI, and he's going to share with us some survey results from that group.
All right, thanks, Greg. I guess I first want to start off and say, how thankful I am to be here. I think I've participated in the audience for every single one of these. I think they may have started out at the Crown Plaza or something early on, so just really appreciate this group getting together and disseminating this information, especially for industry people like myself. We are very spoiled in Ohio to have the likes of Jay Martin, Chris Winslow, Kevin King, Laura Johnson, Greg Labarge. The science community has embraced the topic of water quality in Lake Erie and Grand Lake St. Mary's and really hit it head on. And it's been really helpful for us in ag to have that backbone to bounce things off of, because we really have to do battle a lot of times with our members to get them to go to where the science is going. This is a really different thing for me to do. Usually I'm speaking science to discerning farmers, and now I'm speaking farming to maybe discerning scientists. So it's a little bit of a switch up for me, but I appreciate the opportunity to be able to talk about the information that we've gathered through OACI, and we'll definitely welcome any questions. We'll see if I can wrestle this thing better than Chad did here. Maybe. Oh, so I did a PDF slide, so it's going to be a little harder, so no one can mess with my fonts or anything that I had on here. So OACI is a group of diverse members, organizations all across our landscape. We talk about the cooperation between all the scientists. We really brag about the cooperation between all the ag groups in Ohio. Other states in the Midwest, you don't always get that. Corn and wheat doesn't always get along with Farm Bureau, and soybean and pork and dairy. Well, we have a really good relationship between all of our ag commodity groups, and that really does help have a solid foundation to do big projects, tackle things really head on, like Lake Erie algal blooms. But with OACI, we decided to come together with conservation partners and environmental partners as well. Things that were maybe not as accepted by our members. We've had to come to the table with people who generally, our members have said, hey, they've said some things about us that I'm not sure if we like that or not. And we said, hey, that's okay. We're all going to be on the same page here and go forward. So that allows us not to steamroll an issue from ag groups and not let others who maybe aren't as involved with agriculture say things that aren't necessarily the truth. So, and I will admit this, I've said this in other talks, that you'll hear from farmers a lot to say, well, we feed the world, and they kind of put a period on it. And for me, that's not an excuse to not continue to move up the conservation ladder, to improve, evolve as weather evolves, as climate changes, as your soil type is different, or what have you. I mean, we're seeing things from Chad Penn, and we'll hear things later on today about just how much we don't know about how nutrients move through the soil, how much we don't know about the landscape where our water moves. And it's my job to help kind of keep pushing our farmers forward, because they're admittedly a pretty stubborn group. I grew up on a hog farm in Western Ohio, and I still hear it from a wide variety of folks. Even for OACI, we built an app for this program. And some farmers are able to build the app, 10 times faster than we did, and some other farmers just plainly say, I don't do the internet. So we have to deal with a wide variety of clientele with farmers, and being able to disseminate that information is really, really hard. I'll keep moving forward here. I kind of just said who we are. We have some flowery description of who we are, innovative, collaborative, whatever, but our main thing is we want farmers to move up the conservation ladder. Plain and simple. How do we get farmers involved with programs? invest their own money, help of cost share, whatever, keep moving up the conservation ladder and keep improving what they do because, the food is important, feed is important, but we want to make sure that they're doing it in the best way possible. I don't know, guys. So we'll keep moving past our mission. Again, I'm not huge on sitting in a room and creating mission statements as well. But again, we're trying to bring our stakeholders together across Ohio to help our farmers do better. Obviously, water quality is a huge issue. Nutrient management is a huge issue, and it's not going away. So we want to make sure that we're doing the best we can to help our farmers. So OACI has two priority programs that we worked on. One is a farmer certification program. So that is something that we kind of begged, borrowed, and stole from Michigan, from Illinois, from everywhere. We kind of have a Frankenstein certification program where we want to make sure that we are collecting information from farmers to say, okay, how are you doing? Quantifying their efforts, and then helping them find resources to move up that conservation ladder. That's one of our projects. H2 Ohio participants have to be part of certification. They don't have to be certified necessarily, but they have to be participating in it. And it's a way for us to quantify their farming efforts and make sure that we can have a touch point with them to do stuff in the future to help them move up the conservation ladder. The main one that we want to talk about today is our farm field assessment. So certification was the holistic farm, the holistic farmer, and the assessment is a randomized survey of farm fields in a selected area. So the goal of our assessment was to implement a statistically valid survey across a watershed, and we're trying to establish a baseline. We're not trying to make necessarily definitive conclusions or say, this is great, this is bad. This is the baseline. This is a snapshot in time of where conservation efforts and farming mentalities are in a certain watershed, and then we will revisit that watershed in the future. We went through a randomized sampling of those areas and make sure that we're just not, using a self-selecting group or using, just people who happen to wander into soil and water. We used a randomized sampled group, and the biggest part of this is that they were being contacted by their local soil and water. So obviously with H2 Ohio, the local soil and water was a key component of that connection, the effort that the soil and water's made to get H2 Ohio up and going. We kind of piggybacked on that and said, well, if you're going to have these touch points with farmers, if you happen to have ones on the list that come in, let's get them through the survey. We partnered with the Center for Survey Statistics and Methodology at Iowa State. We wanted to make sure that, okay, if we're going to do this, let's get a model that we can follow each year that we do this survey. So they helped us go through each county's CAUV list, and that allowed us to put a theoretical, throw a ring at the list, and then whoever's in that ring is the randomly sampled ones that get onto the survey. We started with 375 fields, ended up at 450. We gave counties options to go above that. Just we figured if we want to beef up the statistics even more, let's make sure we get as many fields in there as we can. And then there was spatial weighting on the number of fields based on the area of the county that was in the watershed. And then again, the SWCDs were doing the surveying, and then all the farmers and fields were anonymous to the public, essentially, just to make sure that we get earnest and honest participation, and there's nothing funky on there. So for our 2001 survey we surveyed the Lower Maumee Huck 8. We chose this one because we felt like it was the most central and contiguous Huck 8 in Ohio. Considering we're an Ohio group, we felt like for our first time out, we didn't want to wrestle with having to cooperate with Indiana or Michigan to get this data going. Hopefully in the future we can do something like that. But we chose that kind of middle chunk, the heart of the Western Lake Erie Basin to conduct this survey. And we felt that was a good first snapshot of where farmers what farmers were doing in the area. You can see on the right, kind of had the fields broke down by county. And so it just kind of gives you an idea of that spatial weighting that we did across the landscape. So I'm going to kind of jump around a little bit, but first we're going to take a little bit of time to just say, okay, what was the makeup of these fields that we did? Granted, these are farm fields that we did. And so approximately about 66% were involved in cost share. This would be mostly H2 Ohio or EQIP. I think that's a big deal because, mind you, this was surveyed in January of 21, and this was based on what they had enrolled in up until that point. So that was the infancy of H2 Ohio. So even at that point, a randomized selected group of fields in the lower Maumee had us at I think 40% or so. What does it say? Yeah, 48% that were in H2 Ohio already. We would assume that that might be higher as time goes on. But something also to keep in mind, we'll talk about voluntary nutrient management plans and other farming practices. Whatever they had signed up for in H2 Ohio with this survey, they had yet to perform. We weren't even at the season for them to even do the thing. So one of our goals with assessment is to be kind of at the forefront of the watershed when H2 Ohio arrives, and then come back after a few years and see how some practices have changed over time. We obviously know some things are going to increase. We want to see how those other voluntary measures go as we move forward. Areas farmed and ownership status. A couple things that are interesting for us. We have a wide variety of farm fields. We just didn't pick big farmers, small farmers, whatever. We have a good variety of farm fields because we feel like conservation efforts, money for conservation can vary across the board. So we want to make sure that we were well represented. Another one is ownership status. We still are seeing like a 48% owned to 52% leased, but you can see that most of those are in some sort of owned or long-term lease situation. So a lot of times we'll hear, maybe farmer attitude changes depending on how long they farmed a field. And I'm going to bust through these pretty quickly, and I'll be here pretty much the rest of the day if we have questions. Tillage type, about 50% we're doing some sort of no-till or minimally tillage, or you can add another 5% to that for strip till. So something that might change a little bit. This will have been a farm season on the heels of 2019. So probably a little bit more tillage that year because there's a lot of fallow ground, but it'll be interesting to see how that one changes over time. Nutrient source, obviously a hot button topic of how much manure, how much fertilizer. This one seems to pretty much go along with what a lot of people are saying. 86% commercial fertilizer and about 12% manure, so not a large manure watershed. So kind of an interesting tidbit just to kind of see, okay, are we dealing with a lot of livestock or commercial fertilizer? Probably my biggest point to take away from this one, and we want to use this survey as, okay, how can we educate farmers? How can extension, soil and water use this for programming? We're seeing 83% of the farm fields we surveyed were soil tested every 3 years, and then another 13% on top of that every 4 years. So a lot of times we talk about, okay, we need to get our farmers a soil test. They need a soil test. Well, apparently they are. So maybe we can put that one to bed and let's move on to the next thing. How do we talk about using that soil test information for something like VRT or other things? And then along with that, how are they soil testing? What's the intensity of it? And we're seeing grid and zone sampling make up the majority of it. So it shows me a couple things. They have the information needed to do a lot of things, right? They can spatially see how their fertilizer's changing or the nutrient levels are changing in their farm fields. But this also probably tells me that they are dealing with a retailer or a professional of some sort, because that's probably who has been pushing them to do that information. This one piggybacks on the ownership status. 95% of the fields have been managed by the farmer for 3 years or longer. So really important. Our farmers a lot of times will say, well, I just don't know if I can commit to cover crops this year. I don't know if I'm going to do this because I just don't know if I'm going to be farming it next year. Well, I mean, maybe it's because they just don't have a signed lease, which is a problem. But that shows us that, okay, most of these fields are being managed for long periods of time. There's relationships. Unfortunately, maybe it's a handshake deal, but they are the farmer that's there year after year. Where are they getting their fertilizer recommendations from? 66% for the retailer, 24% for the consultant, 9% they're doing it themselves. But again, either way, a lot of that's based on soil test information, based on grid or zone soil tests. So the backbone of that information is good regardless of who it's coming from, but just an interesting tidbit, as we move forward. If they had a VNMP, who was it approved by? So 50% SWCD, 44% they just didn't have one. and then a little bit by NRCS. We would imagine that one's going to go up quite a bit since that's pretty much a baseline requirement for H2 Ohio. But again, they have the information to do it, so it's just a matter of, actually wanting to do it. End placement. This one, again, is just kind of a baseline. I'm not sure how much to conclude from this, but you have surface injection, just regular injection with the starter, and then a starter by 2x2. And then the timing of it, a lot of it's in that early side dress period. But obviously a lot of these are probably happening, a couple times a year, a couple times throughout the season. This is another one we just kind of threw on there as, okay, what's are we doing any sort of water management on some of these? Again, not all fields are eligible for water management structures or water management of some type because of topography. But again, these are baselines, and then the next time I talk about this watershed, we'll be able to do a little bit more conclusions from that. A couple things to take away, just a couple snapshots. VRT technology. 40% of the fields have been using VRT for phosphorus application, and 60% are just the fixed rate. 13% of them were doing some sort of VRT-N, which is kind of an emerging N application. And then those that were doing VRT, they had 31% of them had the capabilities at home, and the rest were done by a retailer. So kind of shows you who's driving some of the things, like some of the previous conclusions we made. Manure applications, so of the ones that were manure applying, 91% of the fields were using the appropriate setbacks, 20% surveyed were using subsurface placement, 77% were incorporating, and then 26% had subsurface manure applied into a vegetative crop or an actively growing crop. So again, take what conclusions you want from that. Again, it's the baseline of where we want to see as a jumping off point. Future assessments, this is our schedule. That's, will probably be changing as we get more funding. We did the Lower Maumee in 21, Sandusky and Scioto tabbed for this year, and then we kind of have a rhythm of every few years and hope to move outside the basin as well. We feel like that's useful information because essentially, presenting information based on a group of farmers who have been just bombarded with opportunity and criticism and new laws and new regulations for the last, decade and a half. So it'll be interesting to see as we move out of there, what's the attitude change on farmers as we move across the landscape. And so we're really interested in that. And we hope that, for the other scientists in the room, grad students, that, this information could be useful for you as well. I will say, I forgot to say it, that we had about a 95% participation in this survey. So for those of you who do survey data, that's extremely high. And that's a soil and water person, either in person or on the phone, inputting the data that the farmer says. So we feel pretty confident about this information. There's not a lot of, you only got the people who return the postcard because they put a little bit extra effort in. No, they were a pretty captive survey group because they were probably sitting in the chair in the soil and water office and like, okay, I'll take 5 minutes to fill this out. So we feel pretty good about that, and we feel like that's pretty rare, and that what this information says is extremely accurate. How am I doing, Greg?
Ready for questions?
Yeah, I have a little bit of an auctioneer style, but Greg gave me the light pretty early. So any questions that you guys have on this information or anything in general on OACI or what we're doing?
Please, so everybody can hear.
Hey, Jordan. So I was interested in the survey schedule that you just showed, and you have like the Lower Maumee, the Auglaize, but then you also have Western Lake Erie Basin as a whole. What's the difference between those?
Yeah, we thought there's a chance to just do the whole basin as we can, just to give that like definitive, this is the whole basin, and we would randomize throughout that whole group, as opposed to doing the Lower Maumee. We didn't want to spread it out too much over time, but we think as it mixed in with the regular schedule of doing the sub-basins, that we can kind of compare and contrast that information and see how it changes. And then hopefully it also gives us a chance to include Michigan, Indiana, if we get a chance and we can get some participation, because we get probably the brunt of it because we have the largest part of the watershed, but it'd be nice to kind of have a really definitive, this is what the Western Lake Erie Basin is participating in.
So you think it'll be like less dense compared to the Lower Maumee or the Auglaize?
Yeah.
Okay.
Yep.
Thanks.
Hey, I was wondering, just looking at a couple of your stats that you had up there from the surveys, what you guys feel about the fact that only 20% of the fields are surveyed are using subsurface placement of manure. It's obviously very expensive, but it's also a BMP that's been promoted very heavily.
Yeah, I mean, the data is the data. I mean, I'm not going to say we feel one way about it or not, but we always want to encourage farmers either get it in the ground, work it in as much as they can. But it's just a touch point for more programming, more education, more demonstration of what's available. And we want to make sure that they're doing everything they can to put it in there. So we hope that we can see a difference as more programming is put forth for those farmers. But we are definitely in favor of that. We just, we don't really draw any conclusions off of it necessarily, besides let's see how it changes and let's do whatever we can to promote that practice.
Greg, this is Chris Wenzel, I have one online. So Jordan, question saying, does STP change slowly enough that every 4 years is an adequate frequency?
Yeah, I think we feel it's pretty accurate. I mean, I think it moves quite slowly. There's some of our farm fields on our demonstration farms not too far from here that they haven't had it move an inch, in years, and they haven't applied any fertilizer in those zones. So, it really is tough, but it's more just you have updated information. It shows that the farmer is doing what they're supposed to be doing. It shows that, that's the backbone of writing a nutrient management plan, of doing VRT, of doing the things that you're doing. So, we think that's an adequate frequency, especially with as you get more precise and have, the technology that's out there. We think that's definitely a good enough frequency.
So the full report is online?
Yeah. Yep, it's oaci.com, I believe, is the website. And if not, you guys can catch me after this, and we can go from there.
And Jordan said he's going to be here the rest of the day,
Yeah.
so let's thank him.
Yeah.
Great, appreciate it, Jordan. Next presenter is Gary Schnicke. Gary is the Soybean Industry Endowed Professor in Agricultural Strategy, Agriculture, and Consumer Economics, University of Illinois at Urbana-Champaign. Gary has a BS in Ag Econ from Ohio State University and a PhD in Ag Econ from University of Illinois, and his research focuses on economics, farm management, and risk management in Corn Belt agriculture. And his topic today is returns from alternative tillage, nitrogen, and cover crop systems, the Illinois Precision Conservation Management Experience. Gary, thanks.
Thank you, Greg, and thank you for having me here. A little other tidbit of my history is that I grew up in Northwest Ohio, spent the last night with my mother, and my brother farms the family farm, and it was in that Huck 8 that was just showing up here. So I have a little bit more interest in this than many other people that are outside the area. I am going to, as soon as we get our slides up here, talk about the precision conservation management experience here that we are going through in Illinois. We have nutrient management concerns in Illinois like you do in Ohio, in the Lake Erie Basin. Ours are a bit different. This slide shows a farm and gives you a view of the landscape of the area that I'm going to be talking about here on our PCM results. I'm going to show you some profitability results from different conservation practices in East Central Illinois. And East Central Illinois is flat, black, corn, and soybeans. As another tidbit, it is not as flat as parts of Northwest Ohio. Many people don't realize how flat Northwest Ohio is. We are, like many areas of the world, very concerned about nutrient runoff from our fields. Our primary concern in Illinois is actually nitrogen, and nitrogen runoff heading down the Mississippi River and making it into the Gulf. There's obviously other water quality concerns as well. We put a plan in place for a 45% reduction in N&P by 2035, and we're coming up to a 15% reduction strategy check-in in 2025, which no longer seems that far away. I want to just give credit for the people that are involved in this. Besides myself, Sarah Sellers is a graduate student, Laura and Greg Goodwin, Laura Gentry and Greg Goodwin work for Illinois Corn, in particular, are the manager of water quality and research. Laura and Greg is the manager of PCM. We also have farms enrolled in this, and we collect data from their farms. I am looking at the economic data from their farms, but there's also part of this field staff that work with those farms, not only in collecting data, but providing recommendations for a variety of things, mainly focused on conservation and nutrient runoff. The circled area there is the area that I'm going to be reporting on, which is East Central Illinois, again, flat and black. And this, like we in Illinois have a good partnership, just like Ohio does, and many firms and organizations and NGOs have supported this project. And if you want to read more about the project, you can go to a publication which is on precisionconservation.org. If you go to Illinois Corn as well, type in Illinois Corn or Precision Conservation, and you will get to the business case for conservation, and there you can get more detailed results of what I'm going to present today. We are going to calculate, and I'm going to show you some economic returns as well as yields and costs, but our major benchmark that I'm going to be looking at is the economic returns from different practices. To give you a feel for what we do, the field staff collect field passes made on each one of fields, and we have about 100,000 acres enrolled, about 10,000 fields. The field staff go out and enter field passes made on those farming operations, and for each field staff there's something a little bit different collected. For example, applying DAP pass, we would know the DAP rate that was implied. If it's a nitrogen pass, we would know how much nitrogen and what form it was implied and whether NSERV was placed on that. And those, so what's collected on each one of those field passes varied. There is not cost associated with that. We are collecting rates and yields. So we're collecting rates and yields, and we're not asking the farmer to provide us the cost for those items. This, by the way, is a pretty typical set of field passes, one for cover crop, one for conventional, quote-unquote, conventional system. The field passes, and vary across these operations a lot. And we tried to, as you're going to see, we're going to classify these, and classifying even what farms do in East Central, and the same would be true in North Central. What they do is phenomenally hard. The other thing is that this 7 and 8 is about the average number of field passes that are made. And it's not only just tillage passes, it's fertilizer passes, pesticide passes, planting passes, and harvesting passes that occur out there. So there's a number of passes that are made across those fields, and obviously the timing and amount of fertilizer put on will have impacts. From that, we do calculate an economic return. All of our returns are based on the standard corn and soybean price and standard prices for the inputs. So if they put anhydrous ammonia down, we said it cost $700 this year, which would be the average for that year. That puts everybody on a standard basis, and frankly, keeps us, I personally prefer that way because trying to get a corn price out of a farmer would be extremely difficult. And it puts everybody, and it would vary, and it puts everybody on the same basis. We're not looking at marketing differences across these operations. And again, we provide them summaries on their aggregate values. The other thing that I'm going to say here is we are going to use the term a lot on these reports called operator and land return, which is crop revenue minus direct cost minus our power cost, and we're going to value each trip across the field at our machinery cost rates that we calculate. And that would be, for each field cultivator pass, that would be roughly $14 an acre. So it's based on a cost per field pass to come up with the operator and land return. We have checked, there's a number of farms in here that are in our FBFM database. It comes out reasonably accurate to what you would see if you would collect prices on average. The operator and land returns is important. It's a return to both farmer and landowner. So that has to be split. And in this area, these operations would own 20% of their land and rent 80%. So, and that, by the way, I would guess is not, I would guess in Northwest Ohio, that's less, you would have more owned, but not, most of these large farm operations will be in that 20 to 30%, 40%. So what the landowner thinks about this all is very important. And this area in particular is very competitive on land rent, much more so than any other area that I have experience in. So there's a lot of competition to be as profitable as possible to pay the highest cash rent. So that's the economic background. By the way, if you're a crop farmer and you don't have rented land, you're not a crop farmer, right? So you got to keep landowners happy. I am going to go through and talk about tillage, what we see in tillage, what we see in cover crops, and then I'm going to give you a summary of nitrogen management. And I realize you're more concerned with algae blooms, but I'll just give you a feel for what we find when we look at those things. First, starting with tillage, and we find, and I'm going to show you this, but a summary of this would be that if you make a tillage pass, we find an economically positive return. And that's not necessarily what we want to find, because we would prefer to see a lot of this in no-till, because no-till would have lower soil erosion, it would have less greenhouse gas emissions, and it would be a lot more, it would have some environmental benefits, which maybe we can capture through a carbon market or something else. But we do find an economic return for one tillage pass. And again, that's sort of a summary of what that all looks like. I'm going to present averages over all those years, 2015 through 2021. You see here we have 18, and this is corn. So this is the crop that's going to be grown is corn. One other detail is these farms are corn, soybean rotations, primarily. So this would be soybean going into corn, 18% no-till, 17% strip-till, 33% one-pass light. All right, one-pass light would be something that's 3 inches or less, leaving a lot of residue on the top. All right, one pass. Remember, we're soybeans to corn. 2-pass light, 2-pass medium, and 2+ passes. We still have farmers that do a lot of 2+ passes. All right, here's the number of fields in each one of those. Yield per acre, and again, these are averages from 2015 through 2021. And I'm going to direct your attention to the bottom at first, operator and land return, and you will see that we have a $320 for one pass light, $328 for two pass light, and then the strip till and the no-till are lower than that, $290 and $298. One item that I would say here is we're looking more deeply into the strip till, and strip till, as we envisioned it, was one pass during the fall, putting nitrogen on in all your inputs, and then coming in the spring and working it. And so we were hoping that that would be capture the tillage benefit. When we're dividing this out now more, and we're almost done with this, but strip till on these farms is practiced in very different ways. Some people do a strip till pass in the fall and then freshen it up in the spring, and some put nitrogen on the fall, some don't. So we got all of that mixed up in that strip till. But overall, and when we take out and make it just one strip till pass, we come closer to the one tillage pass. All right, each tillage pass has additional cost to that. Primary reason why our corn results for the one pass light is if you look at the yield per acre, it goes up from 213 to 219 for one pass light. And again, there's tables in there as well. I would point out that this is from average from 2015 to 2021, and this is high soil productivity rating. Okay, so we find a economic return one pass in this sample, and we have our agronomist Emerson Nafsinger, who's from Pettisville a while, would confirm that his field's trials would say there's a yield advantage as well. This slide breaks down our cost, and I just wanted to put this up here. If you look at field work, which is our cost for field work, 20, 11, 22, 26, and 38. It's a small part of the cost. The other costs are the bigger part of the cost. Just so if you go to no-till, you're going to cut costs, but you still have a lot of other costs. And much of the power costs are related to harvesting. Here's the most profitable fields by tillage cost, just gives you a feel. And then I'll go through this quickly, but it does vary by year. Okay, and again, go to that. We find obviously that soil loss are lower for no-till and strip-till, and greenhouse grasses are less pronounced if we go to no-till. So we would like to see more of that. But right now, there's a return disadvantage there on average. We see more no-till for soybeans, 42% of these fields. So you're seeing a lot of no-till, and then one pass light, and 23% of it are now two pass medium. Remember, this is corn going into soybeans, and our largest return there is for that two pass medium. Again, we see lower yields for no tillage in these fields, and tillage or yields are driving us. Going through our cover crops, 91% of our fields are in reduced tills, and 79% receive some in-season nitrogen application. And it's also important to note here, for our cornfields, if you have a cornfield and planted a cover crop the year before, most of the time they continue to do it. So there's continuation of the process. Same thing for soybeans. For corn, and here we have this broken down by no cover crop, winter terminal, and overwintering. You see our operator land return is $313 for no cover crop, $301 for winter terminal, and $271 for overwintering. The overwintering, you'll notice there's lower yields there as well. And what the cover crop does is sucks up free nitrogen in the soil. All right? And that's the main advantage of the cover crop for our nutrient reduction plan. It sucks up nitrogen. That's converted from organic to inorganic N. Cover crops there, keeps it out of the water bodies. It also makes it not available for the plant, the corn plant. So that's a large issue that somehow, from a profitability standpoint, needs to be worked out. Again, just more detail. Soybeans into cover crops, and we find, and we're more, at this point, more optimistic about making corn, cover crop working from corn to soybeans. And if you want a farmer to start anywhere, start with a cover crop, cereal, rye, corn to soybeans. You still have higher cost and a little bit lower yields. Here you're going to see overwintering 68 bushel yield, no cover crop 70 bushel yield. My reason for why that exists is because you're also doing no-till most of the time. So you don't get the benefit of the tillage on the yield. And when we break it out and do them further breakout and just compare no-till fields to overwintering, we see basically the same yield, but roughly $20 higher in cost. And those $20 higher cost is the seed and the termination cost. Seed, planting, and termination. 20, no yield increase. By the way, that's pretty standard across these studies. So you got $20 of extra costs. Figure out how to get that covered, and this would become a practice. I would note a lot of farmers try it. It is a system change. It's very much of a system change because you're going in the fall. Remember, this is the busiest time of the year for a farmer. I mean, taking off corn and soybeans in the fall is extremely tense. And particularly if you got 1,000, 2,000, 5,000 acre farm, and taking time to plant something that doesn't make money is hard to convince people to do, all right? But they're trying it. Here's what we would say, that we see that as being key to cover crop nutrient loss. We don't see a yield drag when we control for tillage. Key is to keep cover crops in line. You can't have too high of costs. Seeding rates are important. And we're hoping that we can use some environmental benefit payments, government payments to cover that cost so we get more adoption of that. Quickly, nitrogen rates. Prices are high. Prices are really high. They've come down. They're still pretty high. We compared what Illinois farmers do to MRTN. MRTN exists in Ohio. It's roughly 183 pounds, 160 to 183 pounds of N per acre in central Illinois. That would be the rate. My guess is it's roughly similar here. We find a lot of farmers plant above that, but they get a little bit higher. They get a little bit higher yield, but the economic return is sort of. You'll notice it's higher in that 319, 318, in that 151 to 200 pounds of N range, and then it goes down. That's because we're putting on nitrogen that's not covering the cost of the additional yield, usually. So our results confirm that whatever the agronomists that put that together were right, and it's an economic thing to follow. And if we did that, If we had farmers reduce their N rates to that level, they would have higher economic returns by our results. And, whoops, I thought, there's my summary. I'm sorry. I'm having the same trouble as everybody. All right, we got it. My summary. We do see a return to one tillage pass. Cover crops. No yield loss when you control for the tillage impact. And remember, you're going to no-till, which does have, in our results, a tillage impact. We still have higher cost. Got to figure out how to get those come down, and we might see that over time. And we find support from the MRTN put out by the universities. So they're not all that wrong. So I appreciate your time, questions for me, and I appreciate you coming and inviting me back to my home where I could spend the night with my mom last night. So it was good.
Any questions? Chris, you got one headed up with?
Yeah, just from one online. And you hit on it towards the end here. With high fertilizer costs now, have there been any early indications about change in fertilizer application for this year?
So this is a good question. You know, honestly, last year, or now this year, 2022, we don't have data on this yet. You also have to remember there's $6 corn, $6 and $7 corn out there. And I don't think they cut rates at all. I mean, they saw the corn price, they said, let's go. That's my impression. We are in, I don't know where, next year's a different thing, and they're just beginning planning. There's a little bit of sticker shock at fertilizer prices, but we'll see.
Hi, so I was surprised that there wasn't, that cover crops weren't more economically beneficial. And are farmers applying less nitrogen fertilizer given that it's storing nitrogen and usually holding some nitrogen there, or that you're not finding that?
Our results in that study would say that they're not applying more nitrogen on their corn and suffering a yield loss.
Okay.
But think about this, you're taking a cover crop up, it becomes organic N.
Right.
When does it come available? It's maybe not this year.
Okay.
So you got to put more nitrogen on this year. The hope with cover crops is that over time you improve your soil and everything gets better. And the best time it will get better is in a drought year. Give us a 2012 and we'll see if this is all true. But you got to get, the future is now, right? We're only looking at this year's returns, so the benefits may be in the future, and you got to get to the future. These are long-term relationships, but still, you got to make money, and you got to pay cash rent in this part of the world.
Garrett, go ahead, Binayak. One last question.
Hi, I'm Vinayak Shedegar. I'm from Ohio State. Question about your the component where you're putting all the fields into a no-till system or a cover crop as classification. Have you looked at the more specific details about which types of cover crops or how many years of no-till into that system? Because not all cover crops were made equal. If you're using legumes before a corn, then you can definitely get that nitrogen credit.
That's a good point. On cover crops growing into soybeans, we have divided it out, and we're writing a paper now. But the results, it's, in my opinion, our results would say cover crop into soybeans, the best sort of system is no-till. So farmers that do no-till can make cover crops work easier than those that don't. Cover crop, no-till, cereal rye. And then kill it sometime. We have a lot of people kill it after planting. We don't find a difference. Corn, you know, when you plant a legume, it costs more. That's the issue with the legume, and we're still working on that part of it. Again, I would say I would encourage farmers to start with cover crops, corn into soybeans.
Thank you.
Let's thank Gary. And by the way, Gary's headed to Chicago here real quick, so if you got a quick question, individual question, you'll want to catch up with him in a few minutes. Our next presenter, and finishing out the morning session here, is Angelica Vasquez Ortega. She is with the School of Environment and Society in the College of Arts and Science at Bowling Green State University. She has a BS in Environmental Science from the University of Puerto Rico, and both an MS and PhD from Soil, Water, and Environmental Sciences at the University of Arizona. She has research that's focused on biogeochemical processes involving sediment contamination and transport from different land uses and their effect on water quality, investigates how chemical characteristics of soil influence the transport and fate of contaminants. She is investigating the role of bacteria on pesticide persistence and degradation, and examine the correlation between inorganic and or organic contaminants co-transported with dissolved organic matter and particulate organic matter in river systems. So a lot of good work in trying to understand better what's going on in our river systems. And today her topic is going to be the impacts of lake dredge sediments on soil health, some of the agricultural and environmental implications.
I'm petit, so. Good morning, everybody. Thank you so much for inviting me. It's a pleasure for me to be here. And so again, I'm going to be presenting on my research regarding dredge sediments that I have been doing at BSU. Let me see. Okay, so the first portion of the presentation is to say thank you to all the collaborators that has been working with me in the dredge area. So here I have experts from ag economics, microbiologists, ecologists, and also I have been working with consulting companies. So all of them has been working in all the different data that I'm going to be presenting this morning. I also want to say thank you to all the students that are involved in all of my projects. Again, actually I am presenting their hard work. So all of them has been involved, both graduates and undergraduate students as well. So a little bit about dredging, some background information. The federal navigation channels in the Maumee River and a portion of the mouth of the Western Lake Erie Basin, it's being dredged every year. And before July 1st, 2020, most of the dredge that was excavated from these channels was being disposed in open water. It was open water disposal. After July 1st, 2020, that changed, and no longer open water disposal is an option. So it's kind of hard to see, but there is a confined facility, disposal facility, facility number 3, in which now all the dredge sediments are being placed in this facility. So the idea of no more open dredge water disposal, it's because it might exacerbate algae blooms as some of the sediments can redistribute nutrients, and of course we want to improve the health in the lake, so that's why this new ordinance was passed. The state of Ohio is then asking for different beneficial uses of the dredge material. The one that I'm exploring is to use dredge sediments as a farm amendment, okay? So here are some basic characteristic of dredge, we need to explore if the dredge sediments from the Western Lake Erie Basin, it's actually a good amendment. I am comparing here in this table different parameters that are very relevant when we are growing corn and soybean. And in the last column, then we have the values for only dredge. So we can see that dredge contains, if we look at the Bray-1 method, and this can vary depending on the years of collecting the dredge. In this case, it was 38 ppm, which is within the agronomic rate. And also there are other many beneficial nutrients in the dredge. For instance, calcium, it's very rich. So these dredge sediments are going to be contributing to the calcium as well as other cations in the system. So another aspect that we are concerned is this dredge material containing chemicals that can be detrimental to the health of the farm when we put them in situ, in the farmlands. So the bottom portion of this table here, it's showing different heavy metals and cations, and it's comparing that to a regional farm soil. What we can notice is that the heavy metal content, for instance, let's say copper or zinc or cobalt, they are very similar to the background values. So it can be said that potentially there's not going to be a increment in concentrating these heavy metals in soil. Of course, we are also interested in understanding, even though they are background concentrations, these heavy metals will be preferentially accumulated into the different crops. And in order for doing this, I have been studying soybean, corn, and also different specialty crops, such as strawberries, lettuce, tomatoes, and carrots. And all of this data, it's in the making, so I'm going to be presenting to you guys the information that I have available so far. So with that being said, these are the main objective, the overall objective of all the projects that I have in my research. So number one, it's to quantify the effect of the dredge sediments amendment in the soil health and in the yield. Then determine the bioaccumulation of inorganic or organic contaminants in the grains or in the fruits and veggies. And then what I'm doing here, presenting to different stakeholders the results that we are gathering so far. So I'm going to be presenting a series of different projects that are going on or that we have been culminating in my research. So the first one that I want to present is my students did a soybean. They were growing soybean in a greenhouse approach. And what we did is we have buckets with different percentage of farm soil and dredge, trying to mimic some sort of amendment to the field. And so we went from 100% farm soil, 10% dredge, 20% dredge, to 100% dredge. And in this case, again, soybean was the crop. Some images of how the soybean were growing in the greenhouse. This is my master's student, previous master's student that was in charge of this specific project. So this figure here, it's showing the soybean yield and the root biomass as a function of dredge material. We can observe that the statistics for this one, it's saying that there is no significant differences regarding the more dredge, the more yields, but at least the average is slightly increasing as we are adding more and more dredge. The important part here is that there was no loss in yield. At least it was very similar to that of the farm field. What I want to show also is this image of how the root system looked. The more dredge sediment, the root system became more robust. And maybe this is very beneficial to add this type of amendment to farm soils so that the root system can be more robust and it can acquire more water and nutrients as well. A little bit of information regarding the bioaccumulation of different heavy metals. Here is in specific for heavy metals, but we also tested for microcystin and for PCBs and PAHs. PCBs, there was no PCBs in the dredge sediments, so therefore no bioaccumulation. The microcystin concentration in the dredge was extremely low and no bioaccumulation in the grains, specific in the soybean grains. And then for the PAHs, there is PAHs in the soil and dredge as well, but no bioaccumulation in the soybeans. So this data here, it's presenting the heavy metal, and there are differences across heavy metals. For instance, arsenic, copper, chromium, and nickel, there was no significant bioaccumulation across treatments, so it doesn't matter how much dredge is in the system. These specific heavy metals are not preferentially bioaccumulated in the soybeans. The story is a little bit different for aluminum, cadmium, and copper, in which the higher the dredge, slightly higher bioaccumulation of these specific heavy metals. So the next set of experiments that we conducted was planting corn. And again, we have a variety of different dredge percentages going from 0 to 5, 10, 20 to 100%. This is how the buckets look in the greenhouse, and then some data related to that. So for the corn, I don't have a statistic yet. This is something that my students will be working during this semester. So, but what we observe is that there's a slight increase as we are adding more and more dredge. For the corn yield, it was evident that the dredge sediment was very beneficial for the production of corn, and the root biomass also was more robust when we have dredge sediments in the buckets. This image here, it's showing how that biomass actually varies, so we can see that some buckets actually produce very little, and this is why we need to have the next step, which will be put this in a farm field and move to see if these results can also be observed at a larger scale. So this is an image of the root system. Again, we can observe that the higher the dredge content, the more robust that root system. So very remarkable changes in the root system of these plants. So as I mentioned, the next step will be, let's move the greenhouse approach to a field approach. So currently, I am working in conjunction with the Lucas Soil and Water Conservation District and the Ohio EPA, implementing the addition of dredge sediments as a farm amendment in an actual farm. So we have 3 farms, and one is the control, which is being managed as the farmer will do. In this specific case, these farms are organic, so no pesticides or fertilizers are being added. And then the experimental treatments are with 40 tons of dredge per acre, and then the next one is with 80 tons of dredge per acre. And again, no fertilizers. The fertilizer in this case will be the addition of the dredge sediment. So this was a first opportunity and first time of doing such a work, because nobody before, at least in Ohio, has spread dredge sediments in the farm field. So we outsourced the dredge to the farm, that it was spreaded. We used a manure spreader to actually distribute the sediments, and it actually worked very, very fine. We were very happy to see that. And then this is how the fields look right now. So we have different sites with different tonnage of dredge, and by the end of October or November, the farmer will be harvesting, and we will have a better idea of how the yield is changing as a function of the addition of the dredge sediment. So another greenhouse and field approach that we are doing is by planting specialty crops. So again, we have different ratios of dredge with lettuce, tomatoes, strawberries, and carrots. I don't have data yet. This is going right now, but I just want to show you a couple of images of the greenhouse and the field site in which these crops are growing. So much more data to come. So that is the presentation regarding the dredge sediments. So now I'm going to take a couple of more slides introducing a new project that Dr. Jay Martin is leading, and that I am a participant of that project. I just want to add this to the end of my presentation because many of you are wondering the status of this project, and we want to tell you that we are working very hard. Jay is working very hard to make sure that we're moving forward for the implementation of this project. So in this specific project, we are going to have a watershed scale experiment in which about 70% of the area will be incorporating best management practices to reach that 40% reduction in P loads. This is an interdisciplinary work, and the USDA has, well, it's many different pockets of money, but the total is about $80 million for this specific project. So this is an image or a map of the experimental catchment, which is the shallow run that we are going to be using for this specific one. We also have a control one, which is the potato run. Here are the specific practices that we are going to be working with the farmers to see if they can implement. So many of the practices that we also have heard today, the number one practice that we want to enforce the most is the subsurface placement. And then we are going to have different aspects in which engagement with the farmers is the first one. We are going to be ensuring that all the data that it's produced is anonymous. And then we're going to be implementing and monitoring both. We're going to be monitoring the soil health and the water quality. And then the last slide is actually showing all the different collaborators that are going to be involved in this project. So if you have any question regarding the dredge, please ask me. If you have anyone regarding this specific project, Jay will be happy to address those. Thank you.
Any questions? Mr. Winslow.
Yeah, just one. Question about, did you examine the microplastic load in the dredge material?
That's a really good question. I have another professor at Bowling Green State University that he's interested in doing this. We have tried to put a couple of grants. We haven't succeeded having those, but there is microplastics in the dredge, and that will be a very interesting follow-up research. I don't have any data at the moment on that.
Regarding the paired field trials for your dredge application, how was that applied? Was it surface applied? Was it worked into the soil? How was that done?
Thank you for your question. In this specific one, we used the manure equipment, and it was broadcasted. In order to apply the different tonnage, the 40 or the 80, we actually did a soil test, and we apply according to, we never apply more than the agronomic rate, so we never exceeded the 4 ppm of P.
Hi, great presentation. I was wondering, so when you're taking the dredge sediment from like the lake and then going to the surface of a field, you're really changing that redox environment. So I'm wondering if you have an idea of how the geochemistry changes in terms of like the heavy metal, maybe mobility, maybe becoming less or more toxic, or how that affects the plant uptake. Thanks.
Okay, thank you. That's an excellent question. The dredge sediments that are being used currently for this specific experiment or field demonstration were removed from the lakes, and they have been dewatering for almost 4 to 5 years, if that's correct, Vanessa. But that's a really good question. I also have other experiments going on in my research in which I'm actually targeting at redox-sensitive minerals to see how manganese oxides or iron oxides actually are controlling the sorption and desorption of phosphorus. From a previous experiment in which my student targeted these specific minerals, iron oxides and manganese oxides were sequestering a huge amount of phosphate in the soils, very minimal amount of nitrogen. So I will say that if there is any redox changes, changing from anoxic to oxic, in this case, if we are moving more to anoxic ones, those iron and manganese oxides will be dissolved and they will leach phosphorus into the system. I haven't actually look at this as a function of time in a farm as the water table changes, but that will be a really good, to just give me a really good idea for a next project.
Having applied sewage sludge on an 80-acre area, and then seeing somebody else take sewage sludge on a 70-acre area, and we find that trying to spread it, you have to do it before the farmers get in and plant, or in the middle of the winter, or nearing winter, and we had a great difficulty in subsurface injection. We had a high flotation tire, sludge built for incorporating sludge. After about 2 years, it bent the tines because of, even with high flotation tires, you compacted the soil seriously. And the manure is produced 100% of the time during the year, but it can only be applied at very limited times of the year. And so you end up going to surface application shortly after the spring thaw and the spring rains, and that adds, when you're trying to put a product into the soil, changes dramatically when you have to do it over 80 acres with a truck, high flotation tires or what, so you end up broadcasting it with a big irrigation gun. Have you considered that, and what does that do to the utilization?
Yeah, good question. Actually, this has been a challenge to find the specific time in which to put the dredge. Vanessa and Joy, they can be witness of how many times we change the time for the application. What I know, it's an observation from the farmer that it's managing the land for us. He was concerned that we apply at the end of the spring, and he says that because of that, his soil has been more compacted. Another aspect that he is also worried is that by adding the dredge sediments, some unwanted weed is growing in his farm, and this is an organic farm. So we are learning about that, what is the best time. According to this farmer, he will recommend to actually place the dredge sediment in fall, and he's very worried for using the dredge sediments in an organic farm, since they cannot use pesticides to control the weed that might be coming in the dredge sediments.
Yeah. And the other point is, when you have to wait to apply this, you have to put it somewhere. So as a landfill and waste pile management person, when you pile sewage sludge together, okay, works and you have a high rate of ammonia and a very horrible smell that downwind, you get nothing but complaints from your neighbors.
The dredge sediment, it's not smelly. It's actually like soil. If you look at your farm soil and the dredge sediments, you're looking pretty much at soil.
Yeah. So you shouldn't mix sewage sludge and that with dredge material and prepare it to then put on the soil later, because the odor is such that it goes for a mile or so. Okay?
Sure.
Last question, Vinayak.
Thank you.
Very interesting presentation. We're talking about soils, and my question is about soils. You mentioned the dredge sediment is not very different from the farm soil, and I'm trying to think here, the reason it ended up in the lake is because it's texturally different. It's specific particle sizes that end up transporting, and it's highly erodible particle sizes. I'm just wondering if you're looking into the more soil physical properties, particle size distribution type of comparison. And when we apply this on surface, especially 40 tons, 80 tons of sediment on top without any protection for erosion, what that might lead into, especially with heavy rain events that we're seeing.
Yeah, that's something that we have thought about. The Corps of Engineers and the Ohio EPA, they have an extensive report on different physical characteristics of the dredge. I sent the dredge sediments to a lab, and the salt texture is clay, pretty similar to the Hoyville type of soil that we have in the area. I have thought about placing the dredge and then putting some sort of cover crop, but that's, it's more projects to come in the future. Yeah. Thank you.
Let's thank Angelica. Well, I know I've gotten a lot out of this morning's session. Certainly when we think about the Lake Erie Basin that we're dealing with, and knowing the importance that non-point sources of phosphorus going into the basin and the impact of agriculture on that non-point source, this ideal of really looking at it holistically from the farm impacts, the lake impacts, and everything in between is really important. And we're just covering, today just a base skim of some of the topics that we can be. So I hope you got a lot out of this morning's session. I'm going to turn things over to Jay. You have you're on here at 11:40 on my agenda, but let's, Chris, any final things that we need to do here before lunch? You got lunch instructions?
There are some questions online, but knowing that we have lunch served, I will get these to the respective presenters and have those answered and get them back online. You'll note in the back that there are 2 lines, and so go ahead and help yourself. And I guess I'm looking at the agenda that most of you have in front of you, but we'll start back at 12:50, it looks like. All right, thanks, everybody.
so it's down here. Okay.
Oh, yeah, that's
You're in
nice.
here, and the only thing you need is the pink one, the subject forward. From what I've heard, it's a little touchy. Okay. Yeah, just point if it goes, and then we can go back. Let's try some.
No, if it goes too far forward.
Yeah.
Yeah.
We'll get started in about 3 minutes. So if you could grab a drink and have a seat. All right, we'll get going here. Folks want to find a seat. And hello to those of you that are joining us virtually. Wish my kids listened to me as well as you guys are. That's fantastic. Hello, Chris Winslow here, director of 2 programs. So a pleasure of being director of Ohio Sea Grant, the NOAA-funded program, and also director of Ohio State University's Stone Laboratory, so our island campus up on Lake Erie. Just wanted to get some reminders out here before we dive into our next set of speakers. So the first thing is, if you're here looking for EPA credits, there is a sign-up sheet at the front table, so where you came in and got your name tags. So you just need to put your name and your ID and your start and stop time, and so those EPA credits are still available. We are recording these presentations, so for those of you here, but also joining virtually, it's one big long recording right now, but our team will break that up into individual speakers, and it'll be placed on the website aligned with the agenda. So you will be able to find the recording of everything that's transpired already and for the 4 talks that we have coming up. I've also been working to get the Q&As that have been submitted online, and so those that were asked today, great. Those that we haven't got a chance to have answered, I will provide them to the speakers to get those answers, and they will also be posted online for folks to reference later. I do want to, again, just thanks to many, many people. First, for you attendees. It's nice to see so many faces again. This is great. And then also to have folks on virtually. We know that that's a great tool that allows us to get to workshops that perhaps we wouldn't have been able to make otherwise. So thank you for all the face-to-face folks here in the room and the virtual attendees. But again, I want to echo what started our day today with a special thanks to the speakers. So again, the 4 that we've already had and the handful that are coming up. But also that special thanks to those folks that are clearly working hard behind the scenes. So I wanted to thank Shalise again at the front desk, Kristen Fussell, who's also back in the Columbus office, and then Erin Monaco does a tremendous amount of lift. So if you've sent emails inquiring about this event, she's probably the one that's responded back to you. So I just wanted to again thank them. And I also want to thank the Stranahan for this great facility and that great lunch. If you're still hungry, there are sandwiches back there, but we've talked to the staff, and whatever doesn't get eaten today will be donated to a shelter. So know that that's going on. Absolutely, thanks for that. Just a heads up also, so you're going to get a survey post this event. Please take some time to fill that out. What you can anticipate, which isn't different from previous years, but we're going to be asking about your thoughts on topics in the future. And so are there a different theme maybe you want to hear next year when this occurs? Also location, we think that this is a great, pretty central location for folks that come down from Michigan, but also up, from Columbus. I'm seeing thumbs up already. We want thoughts on this face-to-face meeting. I think right now, this is the smallest amount face-to-face when we have been able to go face-to-face. We've been up close to 300 before, but let us know. Is this something you still get value from being here in person? So when that survey comes out. Registration costs will be a question too. We know those are going up, but please know that that's not our intention. It's just when you do hybrid, that AV and other costs and the meals have all gone up. And so please weigh in on that. We do want to hear your thoughts. Also, Greg had mentioned earlier today that the length, when this first started, we had 3 sessions. We've kind of truncated it down to 2. We would love your thoughts on that also. If we go to 3 sessions, clearly that's going to make the day a little longer. But we need to think about, is that something that's important? Last one I wanted to mention too is historically we've had posters in this session too. And so I wondered if via that survey folks can let us know if they want some posters from individuals doing work on the lake or related to HABs that we could do on the side to augment the face-to-face speakers. So with that, we kind of had an ag focus in the beginning of the day, and now we're going to shift over. We're going to hear a little bit about health and health impacts. We'll talk about what's going on in the water treatment space. We'll see or hear an update from the EPA and what they're doing in the HAB space. And then also at the end, our last speaker of the day is from the U.S. Army Corps of Engineers,
And we're going to get to hear a lot of work that's being funded by the U.S. Army Corps of Engineers coming out of ERDIC, and you'll hear that a little bit later today. So with that, I'm going to turn over the podium to our tandem of speakers. So Drs. David Kennedy and Dr. Stephen Haller, both coming to us from University of Toledo. And they're going to talk to you a lot about the health impacts. Just a quick thing about the time that I've got to know both Drs. Haller and Kennedy is these are some not only great researchers, but they just have a great ability to communicate a very complex medical questions they address in pretty lay terms. And so I'm really excited to have them both up here. And I'm happy to announce that they've been recipients of many of the Ohio Department of Higher Education Harmful Algal Bloom Research Initiative Awards. So they're doing some really amazing work. So without any more time, I introduce, it looks like Dave Kennedy's going to start off the talk and probably transition over to Stephen. So close to the mic as you can for the audio. Good. Thanks.
Thank you, everybody. So just before we begin, I'd just like to have some of the members of the lab who are here just stand up and be acknowledged. So Dr. Apoorva Ladd, Josh Breidenbach, Ben French. Also, we couldn't do any of what we were about to talk about without Dr. Dragan Asailovich. Go ahead, you can stand up and say hi. And Dr. Asailovich's team back there, absolutely, incredible, and it's really fun to work with them. So, all right, goals for today. We're going to review some of the current public health data related to HAB toxin exposure, and review some current experimental and preclinical data on exposures, especially in terms of susceptibility. So what makes you at risk? We'll identify some current directions on preventative, diagnostic, and therapeutic strategies for HAB toxins such as microcystin. And we'll just begin with this. Obviously, if you're here, you kind of know this map that HABs are on the rise, and they're not just a problem here. They're a problem across the nation, across the world, and that's really sort of having this. Obviously, Toledo has sort of become a flashpoint. But it's from our point of view, the medical students that we reach, the graduate and undergraduate students are very engaged in this, and they want to do something about it. And so we're going to talk about some of the research that they've been doing. I bring this picture up to show you. This is sort of like the motivation. This was only in 2019. It's not like people haven't known about HABs and that they're bad before, but actually you can see on this slide, hopefully the green circle, there's a sign right there indicating that people probably shouldn't be going in the water. So we have some work to do. So first, let's just talk about what are some of the common target or major target organs for harmful algal bloom toxins. And this is from a review that Dr. Ladd wrote recently that was just published this year. So we know that HAB toxins, just in general, speaking in general, can cause lung damage, so inflammation that can weaken the walls of the lungs. And obviously the liver, people know a lot about microcystin in terms of its hepatotoxicity, but can also increase fat in cells. The liver shouldn't really be a reservoir for fat. So bad things happen when it becomes that. In the gut, we'll talk a little bit about that today in some of our research in the gut. But again, you'll notice a theme emerge here in terms of inflammation and fibrosis. Also in the brain, some HAB toxins can cross the blood-brain barrier. And target different channels, synapses, et cetera, causing, again, inflammation, oxidative stress. Even in the heart as well, leading to inflammation and fibrosis in cardiac myocytes. And then we'll talk a little bit, too, about the kidney as well. Again, inflammation, oxidative stress seem to be some of the common themes. And if you want, we've got the reference there. You can sort of look up that paper. So how do people get exposed? Obviously, there's routes of ingestion. You can think of drinking water, contaminated food, et cetera, but even supplements. This is something we'll focus a lot about today is inhalation and breathing aerosols. A typical human consumes or should, if you're being good to your kidneys, about 2 liters of fluid a day, water a day. A typical adult human breathes 11,000 liters of air a day. So it's a really important route of exposure. And then also dermal contact makes a lot of sense through skin and other recreational activities that would increase dermal exposure. So what can we learn from public health data? So one of the things we wanted to do is sort of see, like, what's the lay of the land? And what can we determine, from what's coming in through our health systems? So the CDC has a nice little physician's reference, and you'll notice down here that they have these codes are called ICD-10 codes, and these are diagnostic codes. These are codes that physicians use really mostly for billing purposes, but help categorize and catalog diagnostic criteria when you come through the healthcare settings. And if you look at these healthcare settings, a lot of them are coming through for HAB exposures are coming through poison control centers, about 3/4, and then some of the other routes there, healthcare providers, emergency departments, and some other. And some of the common symptoms that you'll see are GI symptoms. There's some dermatologic symptoms. And then sort of the catch-all category: headache, fever, lethargy, malaise, etc. So these are what people are reporting when they've been exposed. And this is again data published recently from CDC's Morbidity and Mortality Weekly Report. We're going to focus right now on the emergency room data, and really the reason for this is because we have access to some of that data and its catalog. So what we did was we used these large national databases called HCUP, the Healthcare Cost and Utilization Program. And this is sort of an aggregating service that takes patient information across the country. In this particular case, we focused in on those emergency rooms and looked at that data. And so we looked for symptoms, lab tests, et cetera, and outcomes, again, from these large aggregate databases. We put those into models and then create maps to see what's happening. And this is what we found, and this is data from one of our students, Kat Helminiak. And if you look, this is the years 2016 to 2018, and the emergency visits that came in during those years. And if you look on the right-hand side, so again, the time frame is important because this is the same time frame that the CDC was reporting from those slides I showed earlier. And it looks like for patients who come in to the ER for HAB-related exposure, about 1/3 of them report respiratory illness as their primary code of what they're diagnosed with. Any respiratory illness jumps up to about half of the patients. And then you look at some common comorbidities, smoking and diabetes were two of the most common comorbidities. So we think this is important because it orients us in terms of what we should be looking for. The downside is it's very biased, right? We're only looking at ER visits and only a small snapshot in time, and these are just sort of all comers. So again, this shouldn't be looked at as definitive, but it certainly is an interesting snapshot in terms of what people are coming in terms of HAB exposures. When you refer back to the CDC guidance, one of the things you'll notice is this statement here, and that is tests and treatments for HABs, and that medical care is supportive and that there are no known antidotes or specific treatments. And we think this is something that we can move the needle on, and we want to, and especially in terms of clinically available diagnostic tests. So what are the current experimental and preclinical data for microcystin toxicity and models of susceptibility? And then what are the potential preventative diagnostic and therapeutic targets that we can look to use to help folks who have been exposed? We're going to focus on 3 systems: the gut, the liver, and the lungs. And we're going to focus on microcystin LR as sort of our prototypical HAB toxin. So with the current knowledge gaps is that we don't know who may be at risk in terms of prevention, right? When you think about preventative strategies, you want to identify who's at risk and how can we get the message out to those folks. In terms of diagnosis, right now, a HAB exposure is a diagnosis of exclusion. which, so you have symptoms that overlap with, hundreds of other diseases. So how do you get something specific? We'd prefer to have a diagnosis of inclusion, right? We do a test and we definitely identify that you've been exposed to this or that. And then treatments, what are the therapeutic targets? And we'll talk again a little bit about that. And I apologize for the brevity. This is a lot in 30 minutes, but we'll do our best. So first we're going to talk about the liver. And the genesis of these studies was that, a lot of the initial toxicology studies are done for obvious reasons, done in normal, healthy animal models. But we wanted to ask, what if you don't have a healthy liver? For instance, liver disease, especially non-alcoholic fatty liver disease, it's very common and it occurs about, a third of the population. So we think this is an important and large comorbidity to look at. And if you look at the progression of liver disease, especially as it relates to non-alcoholic fatty liver disease, you can see that it moves in stages from healthy on the left-hand side all the way over to hepatocellular carcinoma. And the important thing about this slide is really that each one of those stages represents the accumulation of hits, I would say. So things that are causing moving and shifting the liver into more progressive disease. And this is some of the data that you're looking at here. These are on the top panel, H&E or slides, and then at the bottom PAS slides looking at glycogen accumulation. And these are livers from mice that have been exposed to who have non-alcoholic fatty liver disease and have been exposed to the toxins. And importantly, we wanted to use doses that were at or around the no observable effect limit for normal healthy mice. And what you can see in here is that there is an accumulation, these large, and I don't know if I have a pointer here, but you can see the yellow arrows and the pointing to the fat accumulation. The liver is not meant to store fat. That's what it does when it has to. And when you store fat, you get lots of beta oxidation, et cetera, and oxidative stress, and that's not good for a liver. So that occurs even at these low doses. This, again, and I'll thank Dr. Dragan Asalovich's lab. One of the things that we did is we looked at excretion of the toxin from healthy and NAFLD, or non-alcoholic fatty liver disease mice. So given the same amount of toxin, what you can see is in the green bars, the healthy animals were able to excrete about 60 times more of the toxin than the animals with non-alcoholic fatty liver disease. So that tipped us off that there may be something going on in terms of the metabolism of this toxin in these different disease states. And again, then now looking at the livers of these mice, so that was urine. These are now liver levels. And again, what you're seeing on the left-hand side is microcystin LR, the intact toxin. On the right-hand side, you're seeing microcystin cysteine, which we'll talk a little bit, but that's essentially one of the degradation products or metabolism products. And what you can see in those green dots on the left-hand side, in a healthy animal, there's very low levels of the toxin within the liver. But when you go through in non-alcoholic fatty liver disease, you see an accumulation of the intact toxin in the liver. And again, on the right-hand side, you sort of see the reverse of that, there's detoxified toxin in the healthy mice, and then in the NAFLD mice, much less of the detoxified products. So we wanted to use an unbiased method to sort of uncover these pathways. I hope that's not me. And one of the things that I'll talk about, again, this is sort of a complicated slide looking at the metabolism, but one of the pathways that we identified was this glutathione transferase pathway. It's a common pathway for detoxification. And we had two drug candidates. One's known and one was lab that we developed in the lab. N-acetylcysteine is sort of the known augmenter of glutathione transferase, and then it's P-nactide. Apologize for the sort of goofy names, but that's one of the lab-derived peptides that we've used to augment this pathway. And push things into detoxification. And this was the protocol that we used. So we put mice on a diet that induced non-alcoholic fatty liver disease. In the last 2 weeks, we exposed them to microcystin. And then in some groups, we gave them either one of these two antioxidant treatments. And what you can see, and this is sort of the money slide here, is that those green dots there show that the inflammation and steatosis and apoptosis scores of the mice that were treated with microcystin and had fatty liver disease, but that was prevented either in the pink or the blue with the antioxidants that we gave them. Also, if you look at urinary excretion, that was again on the left-hand side. The treatments with the P-nactide and to some extent N-acetylcysteine had lowered the amount of microcystin and increased the amount of the detoxified metabolite. And again, this is looking at another enzyme, follows the same sort of pattern. This is that glutathione S-transferase enzyme. And you can see it's depressed with microcystin, but again, brought back to normal levels with those treatments in the pink and blue. So this is sort of the working hypothesis that in a healthy hepatocyte when it gets hit, you're able to detoxify that and survive. The hepatocyte or liver cell survives. In the presence of non-alcoholic fatty liver disease, when you get hit with microcystin, those pathways are blocked and you get liver injury, and we're able to augment those pathways with antioxidants, targeted antioxidants, and promote cell survival and detoxification of the enzyme. So I'm going to turn things over to Dr. Haller.
Thank you. Okay, so let's talk about inflammatory bowel disease, which is everybody's favorite topic right after lunch. That's not a knock on lunch. Lunch was very good. Okay. So let's jump right into some background on HABs and gut health. Inflammatory bowel disease is a collection of disorders characterized by acute and chronic inflammation of the gastrointestinal tract. IBD is a global health burden with an estimated 1 million individuals in the US and 2.5 million in Europe affected. And the effects of MCLR on the progression of IBD are unknown. So we ask the question, does exposure to MCLR exacerbate the severity of pre-existing inflammatory bowel disease? And what I'm going to be showing you here is gene expression of pro-inflammatory markers in the intestinal tissue from our inflammatory bowel disease model. So here we're looking at TNF-alpha expression. This is a known marker of inflammatory bowel disease progression. And you can see there in the orange, in a normal, healthy model, MCLR treatment really doesn't have much of an effect. But when you look at the red bar there on the right, in the face of inflammatory bowel disease or pre-existing inflammatory bowel disease, when you treat with microcystin, you see a significant increase in this pro-inflammatory marker. Similar story for IL-1 beta, another prominent marker of IBD progression. In a normal, healthy setting in the orange, not much of an effect. But with pre-existing inflammatory bowel disease, you get a drastic increase. And finally, CD40, another prominent pro-inflammatory marker. Same story, in a normal setting, not much of an effect, but all the way to the right there, with pre-existing IBD, you get a significant increase after you follow with microcystin treatment. We also noted prolonged weight loss, prolonged blood detectable in the stool, and exacerbated colonic shortening. And this is all in the pre-existing IBD model followed by microcystin treatment. Now, speaking of CD40, so I just showed you that we saw significant increases in the intestinal tissue. So in order to go after this as a potential target, we developed a peptide to actually block CD40 signaling. And that's what you're seeing there in purple. So when you have IBD plus microcystin plus our CD40 peptide that blocks CD40 signaling, you actually get a significant decrease in inflammation, indicating that this could be a therapeutic strategy. Okay, so now moving on to aerosolization. So how are HAB toxins aerosolized, and what are the human health effects associated with exposure to aerosolized toxins? So aerosols are produced by wave-breaking, bubble-bursting, and recreational activity. Aerosols can be carried 30 kilometers from the source, and inhalation of aerosols may occur at the source or a distance. Exposure to aerosolized toxins may lead to airway inflammation. So to take a closer look at this, this is modeling effects of harmful algal bloom aerosols in human lung epithelium. We used a 3D air-liquid interface culture of primary lung epithelium pooled from 14 volunteers. Microcystin LR aerosols were generated by a nebulizer and distributed evenly to the well inserts. And you can see over there on the bottom towards the center, you've got the cilia and mucus layer, the mixed cell population in the middle, and then the well insert on the bottom. Exposure was once daily for 3 days at just 3 minutes per day, and we used 3 doses of microcystin LR, a low, medium, and a high dose. So what we've shown here is that short-term microcystin LR exposure actually significantly upregulates key inflammatory genes in healthy human lung cells. And what you can see there from the bars on the left, the darker blue bars, you see a greater than 2-fold change in genes associated with mixed airway inflammation. And now I'm going to pass things back to Dr. Kennedy. He's going to talk to you about some of the diagnostic and therapeutic approaches we're working on.
All right, so this is, again, this one of the benefits of working at the medical school is being able to, have these conversations with physicians about, how do we move things? What do we do? And so these are some of the conversations that we've followed up on. And one of these is, typically when you have liver injury and you think of microcystin as a hepatotoxin, we want to know, do the common markers that you would measure in that setting clinically, and there are 2 markers, we abbreviate them ALT and ALP. What, can I be monitoring for these in my patients? And so we wanted to ask this question, is this a good marker? Because we saw some of the data from our animal models, and they indicated sort of a mixed bag. And we took that a little further, and we took some human hepatocytes, so human liver cells, and exposed them to different concentrations of microcystin and looked at the expression. I'm showing gene expression here, but we looked at a couple of other markers as well, the protein level, enzymatic activity. And what we saw is essentially for either of these enzymes, there was really no effect with microcystin exposure. And this it's not entirely clear why, but we definitely see in some preclinical models that these enzymes are not good markers, and we think that's important. And essentially, the way I like to describe this is if you hit a hepatocyte with a metric ton of microcystin, you'll see these enzymes released, right? The cell breaks open, and you're going to be able to measure and detect these. But at low doses or chronic doses, we may not see that. And so we think that other targets may be important, and we're following up on those right now so that, in terms of ALT and ALP do not respond to low-dose exposure, and we're working on some other markers, and we'll talk about some of those a little bit later, CD36 potentially, as other ones that may be more specific for, to put in a diagnostic panel. The last thing we'll talk about is a pathway that we're pretty excited about. So you can imagine microcystin LR is one congener of, hundreds of congeners of microcystin, and then what about all the 50, million other things that could be out there in the lake? How do you sort through those things, determine not only what's toxic and what's not toxic, but then how do I develop something to block that? So we have a really cool pathway analysis we do where we can look at the signatures of what chemicals do in a high throughput fashion. And we can compare that to all sorts of any publicly reposited data from toxin exposure, and we can look at the specific signature of what our bad thing of interest, in this case microcystin, does, and look at libraries of thousands of drugs and compounds, natural products, et cetera, that may cancel that signature. It's like you could think about it as noise and anti-noise. And so we did this for microcystin, And you can see the signature that it creates is pretty dramatic. This is looking in macrophages, so immune cells. We identified the anti-signature to this pathway and identified a drug called doropamide, which was actually from a library of FDA-approved compounds. And what you can see here is that we could then specifically test this drug without having to test, go through all the processes and expense. And we could target in on a few drugs that may be able to reverse this. And this is an example here looking at these macrophages, either with TNF-alpha expression or IL-1 beta, which Steve had talked about before. And microcystin really ramps those inflammatory genes up, and doropamide was able to cancel this. So we knew it would do it hypothetically from our screen, and then this is sort of the proof of concept. And this is what we're working through now as our approach as we go through these toxins, because microcystin won't be the last one that we'll be doing. HABs are on the rise and have a significant public health implications. HAB toxins can have both acute and chronic effects, and they affect many organs. Our public health data suggests a need for increased education and awareness, especially in vulnerable populations. And that our experimental data suggests that the common diseases that we talked about in the liver, gut, and even in the lungs may increase susceptibility to HAB toxins. And obviously this is going to help increase our preventative diagnostic and therapeutic strategies. So these are some of the folks in the lab. Andrew Kleinhens, who did a lot of this work, was lab manager. Apurva Ladd, Robin Sue, and Josh Breidenbach, who are here, and Kat Helminiak. Want to give especially a lot of appreciation to Ohio Department of Higher Education and the HABRI funding, without which this, this would not be possible. There have been fantastic supporters, and hopefully we're moving the needle in terms of not just being the city that turned off the drinking water, but being the city who came up with solutions to these problems. So we'll stop there and take any questions.
That was perfect timing. If we remember 3 years ago, Kevin King went an hour when he had 20 minutes allocated, so this makes me feel really, really good. Just kidding, Kevin. Yes, we have about 5 minutes for questions. I didn't see any when I was online there, but I think we're good, so please approach the microphones and engage with Drs. Kennedy and Haller.
Yeah, just a question. When you were talking about the emergency room data and indicating HAB, what kind of HABs exposure? How do we determine HABs exposure? Is it in the water that I was swimming, or I walked through Port Clinton?
Yeah, that's a good, so it kind of points out one of the limitations of that data. So it's, it's HAB exposure, whatever essentially the physician determined as a HAB exposure is. And we're working on a case report now for a number of individuals who have come through our health system, and it's runs the spectrum. And one of the important things about that is that, people typically, at least, and this is anecdotal, but patients typically don't come immediately right after the exposure. So when we talk to our infectious disease physicians, what they see is that sometimes it's weeks or months after exposure or suspected exposure. So one of the things we're really keyed in on is, not what's the blood or the urine test that we can do right at the point of care, because that's pretty easy. If you can determine the toxin at that point, that's sort of a no-brainer. But what can we do months and weeks, afterwards to determine if an exposure has occurred? So that's one of the directions that we're looking at right now in the lab.
So since we got a question coming up. We got a couple minutes, so I'm going to throw one in there while you're coming up. I had the absolute pleasure of listening to Drs. Kennedy and Haller present this already once before. Can you give the audience a kind of an indication when you talk about therapeutics or even diagnostic tests, how long does it take to go from where you guys are right now to something that we might see, right? I don't think this audience may understand that timeline, so if you could briefly jump into that.
Yeah, so the answer is a long time. As you can imagine, it really takes a long time to get something to the clinic because you have to prove that it's safe and effective and accurate marker. So The short-term answer is we feel like we're on the right path, but we've got a long way to go.
I was going to ask to have a what types of markers are you looking for? Like, what's looking promising in terms of identifying that there's been exposure?
Want to talk about that, CD36?
Yeah, so one of the things we found is if you're a fan of the University of Michigan, that's typically, I just had to give some love to Ohio State.
Did you actually know that's where I'm from?
Then you're actually more susceptible to the harmful effect.
No, so it's really important. So what is a good marker of susceptibility? So obviously it's sensitive and it's specific. And that's going to vary depending on the toxin. So we want things that are, so when we're, for instance, with the ALT and ALP, right, that's a very sensitive marker typically for lots of different things, but it's not going to distinguish whether you've had acetaminophen poisoning or if you've had, been binge drinking. So we want something now that's also specific. And this is where, what we're getting into, some of the markers, and I guess this is sort of a research talk, so we can talk about research data. But we've found, so one of the curious things about microcystis, so if you look at normal healthy exposures, people don't talk about it a lot, but you see, even you look at the micrographs, there's fat accumulation in those livers, and they're not being fed a high-fat diet. And so this has been a curiosity to us, and it doesn't maybe not reach the level of clinical significance or clinical finding, but we've keep seeing this either in other people's papers or even in some of our own data. And so we looked at that fat metabolism pathway, and we found a transporter, one of them is called CD36, that appears to be upregulated by microcystin. So again, we'll probably be looking at like a constellation to get that specificity, because you can imagine there's lots of other things. CD36 is a scavenger receptor. It's expressed on lots of different cells. So that might not be the silver bullet, but things like that where we can kind of find the signature, and that's again the importance of doing those arrays that we do in the high throughput screens, is that you can really dial in on, instead of just looking at one thing, one at a time in a serial fashion, we can sort of look at the constellation and go, okay, here's the pattern, and sort of like a fingerprint, nothing else has this pattern.
I was more specifically thinking, Exact Sciences has had a lot of success with their cancer, their poop in a box test, or for example, we've had a couple of spin-outs out of U of M that have had success with urine tests. Roel Chinian's lab did a RNA-based fusion gene for prostate cancer. Are any of those urine or easily accessible sort of sample types? Are there any indicators in those types of samples that you've sort of maybe observed that could indicate HAB?
Absolutely, yeah. So that's the gold standard. You want to have something that's easily accessible. So for instance, CD36 can be shed, so you can measure it in blood. So that's an important potential marker. But yeah, I mean I think you've kind of pointed out the holy grail. It has to be something that you can easily collect from your patient and get that. So when we look through some of these things, if it's not something that is going to enter the bloodstream or potentially be excreted, it's interesting, but in terms of diagnostically, it's not as applicable. So we're trying to take that list and
get somebody to come in for a blood test, right? Especially if they're just think they might have some sort of odd poisoning, but they don't know what it is.
Yeah.
We have one more in the back. Why don't we try and get this one in, please?
Thank you very much. It's a very short question. So the CDC has started this One Health data portal for HABs, and I was curious if you had looked at their set up their data, what they're trying to produce with data product there, and if they ran into the same limitations you had regarding reporting or doctors knowing to ask about HAB exposure. Thank you.
Yeah, so that's actually, we actually got to speak with one of the CDC scientists who helped design that One HABs form. So we're not going to duplicate what they're doing. We're sort of trying to work in coordination with them. There's clearly going to be some overlap, But what we're finding is that, you know, if you look at if you dig into the One HABs data and then some of the state system data, they're actually, we were surprised that there wasn't a whole lot of coverage. And this sort of goes into the next phase of we need to do a better job of communicating with healthcare providers so that there is, you know, they have the information, they know, and there's more uniform reporting, because right now it's sort of like trickles here, trickles there, and it's, you know, that, you know, analogy of looking at the elephant with, you know, lots of different people. I think there is some overlap, but it's not a ton. So it'll be important to coordinate, and that's why we're talking with people like the CDC.
Yeah, and to that point, you're exactly right, and that we have found a lot of physicians aren't even aware of those ICD-10 codes for cyanotoxin exposure.
Great. If you could help me in thanking Drs. Kennedy and Haller. So as I see John Lenhart's making his way up to the podium, I just wanted, the question I asked about getting from where Stephen and David are to where we need to be, I brought that up more to show that the Ohio Department of Higher Education, HABRI, has been great seed money for that, but to get these things from where they are to the next step, Drs. Kennedy and Haller have done a good job of getting NIH and NSF funding to follow up on that. So they've been working hard to continue that work. So our next speaker for us today is Dr. John Lenhart, out of Civil, Environmental, and Geodetic Engineering at Ohio State University. Important to know he's also co-director of the Ohio Water Resource Center, so our USGS-funded center at Ohio State University. And he's really going to talk to us about drinking water using activated carbon. John.
All right, thanks, Chris. Good afternoon, everybody. Thanks for coming out and listening to me talk. Since Chris talked about the Ohio Water Resources Center, I figure I'll send out a plug that we are in the midst of our call for pre-proposals. That deadline is the end of September. So anybody who's considering and wants to ask me a question about that, I am here. If you're not aware of the program, then I'm happy to talk to you about that as well. Oh, okay, I have to pause a little bit, I guess. Okay, all right, so like Chris said, I'm going to talk a bit about some of our work that was done with activated carbon. I'm going to specifically talk about the powdered activated carbon work. But what I want to do to begin with is just kind of roughly talk about water treatment in general as it applies to cyanotoxins and algal toxins. And so when we think about criteria that we might want to use in making decisions about removing cyanotoxins, sort of three broad areas kind of listed here. There's characteristics of the toxin, there's characteristics of the water itself, and then characteristics of the system. So in terms of the toxin, obviously we need to know whether most of the toxin is in the water or in the cell, so intercellular versus extracellular is important to know for removal. Concentrations are also pretty important to know for removal as well, because some processes work better for higher concentrations. Obviously, some are going to work better for lower concentrations. The specific toxin is very important because the properties are different. Their charges are different, their sizes are different, their solubilities are different, and as I'll sort of allude to with some of our results, that makes a difference in terms of how they're removed. And then in terms of the water, the pH influences removal. So subtle changes in the pH that might occur during a bloom season can actually alter the removal and should be accounted for, particularly as it applies to activated carbon or if oxidation is being used, because those are both pH sensitive. The natural organic matter is the big player, as it is for many sort of issues in water chemistry. Natural organic matter is very important when we're looking at absorption processes, competes very effectively with pretty much any organic, algal toxins not being an exception, and we'll talk a bit about that. For freshwater systems, we don't worry too much about salinity, but if you're thinking about looking at estuarine or marine systems, then clearly the salinity is important. It changes the charging characteristics of the carbon, changes the properties of the molecule, how it coils, changes the organic matter properties pretty significantly, has to be accounted for. And then the system characteristics, and I'll talk a little bit more about this, but for the most part, if we think about water treatment systems, there's what I call conventional water treatment, which are the classic unit processes, and that I'll clarify here. Some systems, based upon the conditions that they are facing, have made some sort of modification from this conventional. I'll call that conventional plus. So that's what that designates. Nature of the bloom. are these chronic issues, seasonal issues? That makes a big difference. If it's a chronic issue, then you need to put in some sort of multi-barrier approach that deals with the issue on a continuous basis. If it's a seasonal issue, then activated carbon, like what I'm going to talk about, is what you can use. And then lastly, resources. So if you're looking to deal with any sort of toxin issue, then you need to understand human capital. Is there the intellectual capacity to make the changes? And certainly financial capital. Are there financial resources to make the changes? So overall, just a summary of some of the treatment approaches that can be used. So conventional treatment, as sort of depicted in the corner here, is the traditional approach in water treatment that utilizes coagulation, flocculation, sedimentation, and then filtration for particle removal, and then disinfection for providing a disinfected water. In some instances, you can substitute for sediment filtration with another particle removal process like dissolved air flotation. That's good for light particles, only if the turbidity is low. So if you have a turbid water but it's full of algal mass, it may not work very well. Slow sand filtration is also another substitution that could be made for rapid sand filtration, which is the conventional filtration approach in water treatment. That's useful for smaller systems, but for larger systems, it's not going to be particularly useful. And then in isolated instances, primarily for groundwater, but there are certainly some surface water instances where advanced membrane processes can be used, like ultrafiltration or nanofiltration. And those are differentiated on the basis of the pore size. So ultrafiltration has larger pores. You can get more throughput of water. It's good for removing particles, not so good for removing dissolved things. Nanofiltration, smaller particles, smaller pores. So it's you can remove the dissolved toxins with that, but you have issues with fouling, and then the water flow is low. And then activated carbon. So activated carbon is what we're going to talk about today, and you have choices there depending upon, again, the nature of your system and the nature of the issue that you're facing in terms of using a powdered activated carbon or granular activated carbon. And then different oxidation approaches can be used as well, ozonation and chlorination being the two most common. So if we look broadly at how these different technologies remove toxins, we can see that they have different removal tendencies on the basis of whether the toxins are intracellular versus extracellular. And to a great extent, the ones that do a good job on the intracellular form, so within the cell itself, rely on physical removal methods, so filtration methods. So that's where conventional works, because you are using filtration, coagulation, flocculation to remove particles. Dissolved air flotation works because you are using bubbles of air to remove light particles. Slow sand filtration process, ultrafiltration, nanofiltration, again, using advanced membrane processes. But those don't tend to work very well for the dissolved toxins, the extracellular toxins, and that's where you need to look at something else, such as activated carbon or the oxidation approaches. Those are good for the dissolved, don't do well at all for the intracellular. So for a conventional approach, what you can see is by and large, you tend to get good removal of the intracellular toxins, but not so good removal of the extracellular toxins. So if you're a conventional water treatment plant, you need to look at adding something. And typically, the first thing that you would want to add in terms of cost and ease would be activated carbon, specifically powdered activated carbon. So that kind of gets us to what we did for our research. So we've worked, but we have done some granular activated carbon work, but what I'll talk about is the powdered activated carbon work. And the idea is this is motivated by instances where we're worried about seasonal blooms. The approach is conventional, and so they're looking at scaling up the conventional, adding something to get additional removal, and so that would be the use of powdered activated carbon, or PAC, it's often called PAC. So our criteria for what we were looking at was simply to look at the performance of different types of PAC, look at how operating conditions are important for the removal, and look at how the composition of the water and the properties of the toxin impact removal. And one thing to note is that there is existing literature in this area, but for the most part, the matrix that was used in this literature varies quite a bit. They might go to their local lake or pond, use that as a source water. They might use deionized water. So there's no common matrix in which you could compare rigorously the removal of the different toxins by the different carbons in the presence of different amounts of organic matter. So we looked at things in a very systematic manner, very rigorous manner, allowed us to compare our apples in one case to our apples in another case. And then overall, a goal, again, was to develop guidance that could be used for making decisions for removing cyanotoxins using powdered activated carbon. So specifically for powdered activated carbon, criteria we want to understand would be certainly the pack itself. The source material makes a big difference in the properties of the powdered activated carbon. So whether you're sourcing your material from wood or coal or coconut, which are the most common sources, the subsequent properties of that carbon is quite a bit different. And the differences are somewhat subtle, but they're important to understand. And then the toxin, so I've kind of already alluded to this, the properties of the toxins vary quite a bit. Size, charge, solubility, and that's very important for water treatment purposes. And then water. So for the water characteristics, what we focused on a lot was natural organic matter. We did some work looking at different pH values, but you have to really change those pH values to see significant differences, so I'm not going to talk about those, but it's the organic matter that's really important. And so powdered activated carbon. So here's a cross-section of a carbon particle that might be used in practice, and it's exaggerated a little bit, but basically most of the pore space that's available for adsorption is interior to the particle itself. So the particles are very porous, in essence a sponge sort of a thing, obviously much more rigid. It's not a sponge itself, but the pore sizes are characterized on the basis of some specific diameter cutoffs. So macropores, those are pores that have a diameter greater than 50 nanometers. So for treatment purposes, those are not a particularly useful pore, very big. The mesopores, so those are between 2 and 50 nanometers. So that's a more useful pore size for treatment purposes. And then the micropores, excuse me, mixing up my particle stuff with my toxin work. Micropores are small, so less than 2 nanometers. So your contaminant has to be pretty small to be able to access those pores for removal there. So our toxins of interest, roughly in a cartoony way, are about this size. So we were looking at microcystin and saxitoxin. And then I have iodine up there because iodine is often used commercially to evaluate and compare sort of the active surface area of carbon. But it's a much smaller molecule than are the toxins that we're interested in. So if you look at where these might access in terms of a carbon, this is again shown in a very sophisticated way here. So for the mesopores are sufficient in size to allow for the entry of microcystin and saxitoxin because of the size. So microcystin has, depending upon which way you look at it, a size of 2 to 3 nanometers in diameter. Saxitoxin is quite a bit smaller. We're talking about the order of a micron, or a nanometer, excuse me. Iodine can access all the pore spaces. So again, when we're looking at carbon, it's important to understand the properties, specifically the porous nature of the carbon, because that will factor into how well it removes or doesn't remove. And then secondarily, there's other properties of the carbons that differ. So charging properties of the carbons can differ depending upon the source, depending upon how it is activated. But for the most part, I'm not going to elaborate too much on that. So here's briefly the toxins that we looked at. So we have saxitoxin. So it's neurotoxic. Microcystin, we specifically looked at LR. That's what I'm going to talk about, but we have looked at other microcystins. Important things to note are the size. So saxitoxin is about 300 grams per mole in its molecular weight. The microcystin LR is about 1,000. So there's about a factor of 3.5 difference in the molecular weight, and that sort of translates to size as well. Charge. So the charges are different for these two toxins. So saxitoxin under normal water conditions has a positive charge. Microcystin LR has a negative charge, and that is important for water treatment purposes. And then organic matter. So organic matter, it complicates removal quite extensively because it competes with the toxins. And organic matter, if you're not familiar with it, is a heterogeneous mixture of naturally occurring organic molecules that are in the water from the degradation of plant and animal matter, and the properties depend upon the watershed. You could have microbial organic matter or terrestrial organic matter, or a mixture of those. So again, here's our carbon, here's our microcystin and saxitoxin. Here's our natural organic matter blobs, molecules of different size, and it competes. So the idea being that in treatment purposes, if you have organic matter, you have toxins, those are all going to be attracted to your carbon. And the different sized organic matter molecules, the organic matter molecules that have different properties are going to compete, and they can block the pores, hindering the entrance of the contaminant to those pore spaces. They can actually also absorb to specific sites where those contaminants might absorb as well. Competition varies. So I want to summarize some of our results, overall trends that we saw. So this diagram shows what I'm calling the relative removal rate. So that's on the y-axis. And then this is on the basis of microcystin and saxitoxin, and we looked at a variety of different carbons. So this is our nominal water. It has a pH 8, 8.25. In this case, we have a TOC of about 5 milligrams per liter. Maybe a little elevated, but not out of the realm of possibility during a bloom. And so the relative removal rate is just the rate constant. And I've normalized it to, in this case, I've normalized it to the smallest one, which is the one for bituminous coal under the microcystin LR. So that is set at 1. So that's our nominal rate. And so you can see then on the basis of this that compared to the bituminous coal for microcystin removal, that the wood-based carbon removes about 12 times faster or 11 times faster. So the rate of removal is much quicker with the wood-based carbon than it is with the bituminous coal. Other thing to note is the removal rates for the microcystin vary quite a bit depending upon the carbon. The removal rates for saxitoxin, however, don't vary a great deal, only a factor of 1 or 2. And so if we think about our carbon, this is kind of what depicting it. So the wood-based carbon is, it has a high surface area and it has a high concentration of mesopores. So on that one side there, I have wood carbon, significant medium-sized pores. So it's got the mesopores. On the other side is coconut. Coconut has a high surface area, but that surface area is all dedicated to very small pores, the micropores. So if you're a contaminant that is very small, then you can access the pores in the coconut. If you're a contaminant that's not very small, like microcystin, getting into those pores in the coconut's a challenge. So the coconut, by and large, performed terribly for the microcystin. It's just microcystin can't access that surface area, can't be removed with the coconut carbon. Wood carbon works very well with the wood-based carbon. It has a lot of mesopores. The wood carbon actually also worked pretty well for the saxitoxin. Even though saxitoxin is smaller than the microcystin, its ability to get into those mesopores and some of the micropores allowed it to be removed pretty well. But since it wasn't being cut out from a certain set of pores, the influence on the carbon properties was lower, and the rate, impact on the rate was lower. So the toxins themselves. So here we're looking at the affinity, the partition coefficient, KD. Thanks, Chris. And two things to note here. One thing, so it's a log scale on our y-axis. So what we can see is that the microcystin is attracted to carbon about 3 orders of magnitude more than the saxitoxin. So microcystin is therefore going to be removed much more readily with activated carbon than is saxitoxin. And then the reason why is a couple things. One is the solubility of these molecules. So the saxitoxin, even though it's smaller, can theoretically access more pore spaces. It's more soluble. And so that solubility then translates to hydrophobicity. So it's a lower hydrophobicity compared to the microcystin. So the microcystin is more hydrophobic, and it's more attracted to the carbon. And even though it may not be able to access all the pores, it still is removed to a greater extent than is the saxitoxin, by and large. One thing to note is variations in the properties of a specific class of toxin do have impacts on removal. So we have looked at different microcystins, and there are variations that we see depending upon the specific microcystin. They're more subtle than these sorts of trends, but we do see differences depending upon the variable functional groups on the microcystin. Composition, so again, the big thing with water composition is organic matter. So here we have shown removal rates again as a function of the amount of organic matter. In this case, we're presenting the organic matter concentration as a TOC. So on one side we have no organic matter, so that's the 0 TOC. On the other side we have 5 milligrams per liter of TOC organic matter of about 10 milligrams per liter. And the rates you can see go down pretty rapidly as you add organic matter into your system. The organic matter is competing. And then the impact on the rates of removal are also different depending upon the carbon. So the wood-based carbon is impacted less than the other carbons are by the presence of organic matter. So you can see in this case we actually got some removal with the coconut if we didn't have any organic matter in this system. That's a tiny little yellow bar. And once we have some organic matter in there, the coconut doesn't work at all. So again, this is a competition thing. So I'll just quickly go through there and try to summarize. So in general, for all the toxins that we looked at, the carbon that had the most medium-sized pores, the mesopores, worked best. To some extent, this is counter to some of the literature for saxitoxin, which had shown that carbon, like a coconut, might work pretty well. Coconut didn't necessarily work very well for us. Maybe there's other sources of coconut that might need to work better. The microcystin LR was more dependent on the carbon source and properties than was the saxitoxin, so we saw relatively similar removal of saxitoxin with our different carbons. The microcystin removal varied quite a bit depending upon the carbon that we used, and again, that's a function of the properties, the pore spaces in particular. And then microcystin was also influenced much more than saxitoxin by organic matter. I didn't show the results, but saxitoxin competition with organic matters is much lower than is the microcystin. And we're not entirely certain why that is. We believe it's a function of the charge. Saxitoxin is a positively charged molecule. The microcystin that we looked at was a negatively charged molecule. Natural organic matter molecules are by and large negatively charged, and so you get more competition if they have the same charge. Things to consider just to wrap up. So cost of carbon versus dose versus time. So the idea being maybe the wood-based carbon is a little bit more expensive, but it works more quickly and you don't have to use as much. So maybe there's some sort of costing that needs to be done there. Availability, so we tested locally sourced carbons. Their literature has carbons of all sorts of sizes and shapes, sourced from all sorts of places, processed in all sorts of ways. We did not do anything particularly special to our carbons. They were all commercially available, all sourced locally, not esoteric as well. Treatment, so in terms of making decisions, whether to alter treatment, it's important to understand that in many cases, people are more comfortable with what they're using, and that's fine, but have to understand the limitations of that and whether there are alternatives that are better. And then residuals, not talking about residuals, but certainly the residuals have to be managed. If you're using powdered activated carbon, those toxins then get associated with the water treatment residuals, and then there are secondary issues associated with that, which I think some people are looking at, but not talking about today. All right, so acknowledge again, Sea Grant, ODHE, some laboratory facilities at Ohio State, and several students that have worked on this, Ashnika, Yenling, Kate, and you, Joe, as well as some undergraduates, Emily, Nate, Abby, Alex, and Kaya, and now, I'm sorry, but maybe I have a minute for questions.
Time for a question if we get to the microphone. Do we have one?
Municipal water treatment plants, where are they able to source the activated carbon from? Like, where does the wood activated carbon come from?
There are local vendors that you can contact, so sales representatives for like Jacoby Carbon and Calgon. So these are all commercial ones, and so where they're getting that wood from, that I don't know. Like specifically where it's coming from, that's not a question that I asked. Is that kind of what you're wondering, or? Well, I think in some cases it is actual virgin hardwood. I think in other cases, mostly it's sawdust, byproducts from other wood processing. They get that and then are able to turn it into activated carbon. But that would have to be specific to the source, and you'd have to ask the salesman, and maybe they tell you, maybe they wouldn't. Might be proprietary. Okay. Yeah.
Yes. Where do you apply the activated carbon? At low service before it comes to the plant? Or do you put the activated carbon after softening and changing the pH back up to about 9.5?
I think by and large, the earlier the better. Most of the conversations I've had with utilities is they're trying to put it in at intake, so it mixes as long as possible before they actually add the coagulant or cease settling. So you want to try to add it early so you get that contact time.
Okay.
Okay. All right, thanks.
Thanks. Join me in thanking Dr. Lenhart. I just want to point, thanks for the acknowledgments for Ohio Sea Grant, but those Ohio Department of Higher Education funds are co-managed by both Ohio Sea Grant and the University of Toledo, and so that's been a great partner through time. Next, I get to call up Amy Jo Cly with the Ohio EPA, so she's the Chief of Drinking and Surface Water. No, drinking and groundwater. Very different than surface water. The name suggests that. So Amy's going to come up and give us a great update on what Ohio EPA has been doing in the HAB space. And she's got an amazing team that Ohio Sea Grant gets to work with all the time on helping to identify HAB's priorities. Should have said that earlier, but the Ohio Department of Higher Education RFP that goes out for HABs is entirely driven by our state agencies, and it's that engagement that makes the results of those projects so impactful. So thank you for that. Amy.
All right, well, good afternoon. If folks if you need to stand up, we had lunch, it's been in technical talks, we've got less than an hour to go, you can do it. How's this clicker work, Chris? Oh, okay, you even color-coded it, okay. Well, as Chris mentioned, I'm the chief of the Division of Drinking and Groundwaters, and I have the privilege and the honor to represent the work of so many people. There's a lot of folks here from Ohio EPA today, including our friends at the Division of Surface Water, as well as I think some of our folks from my division and others. So I want to thank you guys for the work that you've done. The story we're going to tell you today is in part a lot of their work and efforts. It's also a story of partnership and collaboration with Sea Grant, with Ohio Department of Natural Resources, with Department of Health, with other researchers. It's really, as I was kind of reviewing the talk for today, thinking about the story of harmful algal blooms in the state of Ohio. And it feels like we've been doing this forever, and it's not been that long. It was 2010 when kind of the first chapter kicked off with Grand Lake St. Mary's, and we got reports from a federal national lakes assessment report that says there was toxins, and we're like, what is this? And right before Memorial Day, and there's going to be 30,000 recreators on the lake, and what as a state do we do? And it's about an emerging science. It's about since 2010, think about what we know today in terms of how we treat and remove, how we deal with the phosphorus in the fields. It's really a very quick read story in some ways of the speed at which it's progressing. But after that initial event, we worked as a state to get a strategy together. And again, we worked with the cross agencies, Department of Natural Resources, Department of Health, and pulled together the state's first HAB response strategy. Initially, we had public water supply and recreational response wrapped into one. In later years, we would separate that out. But it's an evolution. Of course, in 2013, we had a small system on Lake Erie that had some detections above our action level. And then 2014, we had an event up in this area with the algal blooms here in Toledo. And a real important foundational moment for Ohio's program is in 2015 when Ohio Senate Bill 1 was passed. And that was a legislative mandate to put together a program and establish rules that our agency put together for public water systems. And lots of work. And at the same time as a state, we're trying to figure out how to respond to this. There wasn't a lot of federal guidance and a regulatory framework established. We're still waiting on, I think, pieces of that to happen at the national scale. So along with Ohio's story, we have some pieces coming out from the federal government. 2015, we got some drinking water guidance from microcystin and cylindrospermopsin. 2016, our rules went into effect. June 1st, I think it was, 2016. And then again, 2019, we had a federal release of recreational guidance for microcystin and cylindrospermopsin. And then we've been evolving, we've been learning, we've been coming to conferences, we've been working with researchers, we've been talking to our systems and updating our strategies and most recently our rules. So it's really hard to believe that this is our 7th HAB season that we've had with our public water systems with our rules in place. That's a lot of time. It's also a lot of incredible data that we've collected over 7 years. We have around 120 water systems that utilize surface water that are subject to this rule and have been having to do the compliance monitoring. And so we do have our rule package, and for those who are interested, the Ohio Administrative Code, really comprehensive rule set, and for those who worked on these rules back then, we got a lot of things right. A lot of things have held this test of time. We had monitoring requirements. We had some really important pieces about proactive efforts or preventative efforts to get our water systems prepared. So if they did have a bloom, that we were able to optimize, and I'll talk a little bit more about that in a minute. We also have the laboratory part, certification, the methodology. A lot has changed since we started this as well in terms of what's available, the detection limits, different toxins we can test for. Just kind of want to set the framework for where we are. These are our current drinking water action levels. We have a 2-tier system. These haven't changed recently. Again, we are waiting to see if federal numbers come out. We still don't have federal drinking water standards in terms of MCLs or things that we traditionally see. But here, just for reference, these are our current numbers. They are included in our strategy. So I mentioned this incredible data set that we have, and as part of our preparation for revising the rules, we wanted to analyze and look at that data, and what is it telling us? Are there trends? Are there assumptions that we made about occurrence? And where are we seeing it in the state? So the next few slides I'm going to show you are an analysis of 2016 through 2020 data. And so this is a snapshot of microcystins in drinking water sources. And you can see where we've had them detected. And then the blue dots are where the gene is detected. An important aspect of our monitoring scheme at our public water systems is we are doing some testing for microcystins, so the actual toxins, but we've used qPCR as a screening tool, and that is telling us where genes of different toxins are present. And we have in our protocol, we'll do follow-up if we're seeing genes, and we've learned a lot through this. So you can see for microcystins where 67% of those around 120 systems have detected microcystins. 77% had the genes. So around 10% of the time, we have systems that have detected the genes, but we didn't see the toxins in the follow-up. We're learning a lot, I think, through the science about the co-occurrence between the genes and these other indicators and the actual toxins. The other thing I want to point out is we're here in Toledo, but this isn't just a Lake Erie problem. It's not just a Grand Lake St. Mary's problem. It's an inland lake problem. It's a slow-moving river problem, an impounded lake problem, an Ohio River problem. Heck, I was hiking in Colorado a couple of weeks ago, and I'll be darned, my hike was ruined by algae on a lake. I'm like, I can't get away from it. The other thing we looked at was, in terms of our water systems, do they see it routinely? Does it repeat season after season in terms of detecting microcystins? So this graph is showing raw microcystin detections at our public water systems. And on the far left side of the graph, of our systems for the 5 seasons that we evaluated here, how many only had it detected one season? And that was about 25 of the systems. And then on the far right of the graph, these are the number of systems that had it every single year out of those 5 years that we evaluated. Again, quite an extensive data set. I'm sure there's researchers out there that are going to do even more, can use the information and data that we have along with some of your occurrence evaluations. But over 26,000 microcystin compliant samples. There is some good news to the story. 96% of our raw data, our testing, was below 1.6, which is the upper threshold. 36% of our systems that are subject to this testing have never detected microcystin in their raw water. Saxitoxin, along with other toxins, additional toxins, are ones that we're taking a closer look at. As I mentioned, we've got the gene testing, the screening, and so the dots on this map represent places where we've had the genes were detected. But then in the follow-up sampling, you can see with the green, yellow, and orange where toxins were found. So if we had the genes detected and we went and did follow-up toxin testing and we didn't find it, that would be the blue dots. So a smaller rate of when we have saxitoxin genes to finding the actual toxins when we do our testing versus the microcystin. So we had about 75 systems that have had the genes detected, but at 35, we found the toxins present. We often find them at very low levels. Again, it's about the timing of when the genes are expressed, when we're detecting them, the delay to when we get back out and do the follow-up testing, the dynamics and movement within a lake are all really interesting things that we're trying to learn even more as we go forward. We've also looked at the seasonality across the state of what we're seeing with microcystin detections. And this is just a seasonal count, month by month, of our microcystin detections in raw water. And one of the questions we asked, and this was as we worked through our rules, did we have the season calibrated right for Ohio? And based on the data, we ended up, and I'll get to that point here, but we ended up shifting the season by 1 month, just based on occurrence. So every 5 years, we have to review our rules at Ohio EPA and determine if any changes are needed, or we refile them with no change. It's just part of the life cycle of rules in Ohio. So that's a coming of age story for the HAB rules. This is their first revision, and it was a great time. I think it was the right time to look at them and that we had data to look at. So we've made some adjustments. These were recently, I think, finalized and posted. But as I mentioned, the methodologies have evolved, and so we've incorporated the updated methodologies into our rule. The cyanobacteria screening, I think, has been a really valuable part of our approach in monitoring at our systems. And we've made an adjustment in the rule that allows us to use other methods in the future. The previous rules relied on qPCR only, and I think anticipating that methods and tools are going to evolve, we wanted to open the door for other options there in the future. I mentioned the proactive or protective pieces of our rules, and that was requiring public water systems, if they had any detections, that they needed to put a treatment optimizational protocol in place. So they needed to have a plan. If we have toxins present, what can we do immediately to optimize our plant to reduce those toxin levels? And that's been very successful. All but 27 of our systems have already triggered it because they've had detections. And because they also need to, if they're a surface water system in the state of Ohio, they have to have contingency plans for emergencies. And one of the scenarios they have to address if they're surface water is a HAB event. And a lot of that is the same information. So we've just are requiring the treatment optimizational protocols, preparedness for all systems going forward. And then one of as I mentioned earlier, the seasonality and what we've looked at, we've shifted the season 1 month later, and this will go into effect for next HAB season in 2023. And again, it's based on the occurrence data. Really saw the bulk of the blooms between June and November, so it's going to be shifted in a year. it'll be shifted starting next year by 1 month. And one of the things we tried to do with the rule changes was striking a balance between the burden and the cost to public water system with ensuring that our monitoring was capturing when there were issues and we could get in front of it. There's a balance, because implementing these rules is a cost to our communities and our public water system. So that's was kind of our focus all along. So I want to shift gears for a minute and I also want to talk about the rec side and some of the other things that are going on. But just a real quick flow chart here of how we respond, our response strategies. And, for the recreational side, we have visual observations coming in. Our team does reviews of satellite imagery. We get bloom reports. There's different ways there's a lot of ways for us to get a notification. We could go collect a sample and then potentially post advisories at beaches or waterways. Public water system, again, we've got the screening, and we also have the actual microsystem testing, and then the screening can trigger testing of the other toxins. So I want to give due to the rec strategy, because that is a really important part of our work as a state. So this, again, is a joint effort with Department of Health, Department of Natural Resources, and Ohio EPA. This strategy, like our public water system one, has evolved and changed as we've learned about communication. We've adjusted numbers, we've tweaked our signs, and we've got new ways for the public to communicate with the state. These are the latest numbers. The latest change in the rec strategy was in 2020, and we made some adjustments at that point to the advisory numbers. You can see those here. This white sign, I think, was in a photo in an earlier presentation. It was real small, but it was there, and you've probably seen them at our state park beaches. This sign does not change. This was one that we've had for a while. But a new one that we added in 2020 was this really cool blue sign. And this is all about messaging to the public. If somebody goes to a beach and there's a visual of a bloom, but we don't have data back, we wanted to inform the public that there's something going on, we're investigating it, so the public can make decisions of their own. So that's why this sign was created. Templates for all these signs are available on the website, but this was kind of a new wrinkle we added in 2020. And then we have the standard red sign, which is driven by actual toxin levels. And then the safety green sign was another one. This is another challenge of communicating on HABs to the public. People enter the water from different places. There might be boat ramps, and then they may drive over to a beach, or they may enter, at a ramp where there's no blooms, but they might be recreating over where it is. So again, this was designed to try to educate the public before they enter the water and can make decisions if they come across the bloom. There's the link for the Beach Guard website as well. I want to just give a shout out to ODH for the Beach Guard. If you ever looked at this is where they post all the current recreational advisories, real-time data behind it, and informs Ohioans of what the status is of beaches before they make their plans. So I'm almost done here, Chris. I don't know how much time I have, but this is a lot on this slide, but I think it really links with a lot of things that have been said today. Maybe not directly, but in the big picture, synergistic way. We are a part of the funding mechanism in terms of some of the funding we have available to give out, in terms of grants that we've given to public water systems to buy their data sondes and monitor. Of course, we do infrastructure funding. We've had targeted funding to help with harmful algal blooms. The City of Toledo and others have been a big part of that. We do a lot of technical assistance. Again, my team in the room, and there's a lot that aren't here today, have been, Friday afternoon, we've been shooting out to water systems, making sure that we're doing everything we can to guide them and help them deal with what might be happening in their water. I want to call out a special project that we did too with US EPA. We were part of a pilot project selected nationally, and we did comprehensive performance evaluation, CPEs. And this is a very intensive effort. It was a joint effort between US EPA and our team and the water plant. We went to 4 water plants in Ohio. It's a week-long effort. You look at from head to toe of the water plant, operations, treatment, complete investigation, and it was all focused on HABs and optimizing and operations at a water plant. US EPA has used that nationally. We're really proud to have been a part of that effort. Emergency response, I mentioned. We, again, have HAB incident action plans. All of our water systems have contingency plans, and we've done some tabletop drills and exercises statewide to make sure we're ready for whatever comes around the corner. The one thing I've learned from HABs is don't get comfortable. You don't know what's going to happen next season. As soon as we think we have, they're like a teenager. As soon as you think you have them figured out, then it won't work and they completely change. I also want to shout out to my surface water friends here in the room. Within our own agency, we have looked for ways to integrate the Clean Water Act work and our Safe Drinking Water Act. And so how can we, and a lot of the work we do with nutrient reduction in streams and wetlands, how does that tie directly with source waters for our public water systems? And there's an absolute direct link. We've incorporated that into our integrated water quality report. And we even have indicators of impairment tied to toxin levels, and that's something we're going to evolve even further in the future. And then finally, research. I know from a state perspective, hearing all of these, and it was, I don't know if you did it by design for the conference, but from the source, the phosphorus, to what's happening in the fields, to what's happening in, in the treatment ditches, to what's happening in the lake, to Dr. Lenhart talking about treatment. As a state, that has been so invaluable for us, and I think I speak for my sister agencies as well, what that partnership has meant. So, as I look back at Ohio's HAB program, I'm really proud of what we've done as a state. I think we've grown a lot since 2010 when we started this story. And I think it's because we're here at events like these. First of all, these events are happening in Ohio, where you've got state practitioners and administrators listening to the researchers, and we're learning from other states, and we're applying that into what we're doing with our programs. And we're also applying that into identifying what the research gaps are. As Chris mentioned, we are helping to inform where those gaps are, so that impactful research that you're doing, we can have the immediate application. And then partnership. I think today is a total visual of the partnerships, and I really appreciate that, whether it's with US EPA, with our water utilities, with our local communities, and then, across-wise, even, the ag folks. I even understand, some of the soil science, and I'm starting to understand that soil equation thing, But it's all important because it's all connected. So we, as a state, are looking to remain as a national leader. We get calls. We love getting calls from other states asking us what we're doing right, and being, I think, a good support for others around the nation, and we want to stay in that position by continuing to come to events like this. So, with that, I want to close out. Here's our team for harmful algal blooms, especially with the public water supply response side. Colin White is our manager down in Central Ohio, and then we've got a whole team of folks spread across the state to help. With that, that's it. Thank you.
We have time for a question or two if we have anybody.
Hi, thanks. That was a really good summary of kind of what's been going on, and I wanted to ask a little bit about the recreational signage and alerts to the public. Have you heard any feedback, either from your managers at the local level or from the public, about kind of the different signs that you're using in the time period? I'm thinking about, some parks managers and folks that that I've worked with in the past who would say something like, how do I have the capacity, or how am I supposed to have the capacity to change my sign every day, or wait for lab results, or make sure that things are timely, but not confusing to the folks who are visiting those recreational areas?
That is a fantastic question. And it's one that we've talked a lot about internally. Our partners at Ohio Department of Health, we do trainings at the beginning of every season with their park managers. We've met with, through Ohio Department of Health, the local beach managers and local health departments. But again, the timing, it's like, do they have, if they're responding to a bloom, time to run out? And so we've tried to make it as easy as possible with templates. I know ODH fields a lot of questions. I think we get some, and if there's an event going on, additional support. We did, in the last 2020 version, we added a new section to the back on local response. So tried to put together kind of a rip and run game, response plan to make it even easier for locals to respond.
I was wondering if you could break down you mentioned that it was a lot of cost for the individual water treatment plants. Could you break down in terms of what's the total cost to the system, if possible? And then also, where does that cost sort of come from? Is it collection? Is it transport? Is it the actual paying for the test? Not exact numbers, but is there just sort of a ballpark where those costs come from?
Yeah, as part of the rule review, we have to do a cost benefit analysis, and I think we have ballpark numbers in that. And primarily the cost to comply with the rule is tied to the monitoring, and it's extensive tests. They add up, especially during the season. But I do believe we have some estimates in there in that benefit analysis. It should be online with our rule package. If you can't find it, please just reach out to me and I'll let you know. We did also, the other cost of HABs to public water system is in treatment. And we've recently done a survey not too long ago about what is the cost to manage these at the water treatment plant. And I'd have to check on it. You can send me a message and I'll track down where that went. I think there was an article that came out from another group recently looking at the results of that survey.
I can definitely look up where that document is to get the ballpark numbers, but I probably doesn't have breakdowns for where those costs exactly are coming from. Do you have any feeling for between testing and remediation and collection, like ballparking where those costs are coming from?
I don't have the ballpark numbers in front of me, but I will definitely track them down for you.
Just a quick one from online. Why is the Ohio saxitoxin threshold 1/10 that of the microcystin level?
Why is the saxitoxin number lower? It has to do, I think, with the toxicity assessments and health assessments and I'm not a toxicologist, but in our strategy we have an explanation of exactly where that came from and the federal guidance numbers that we plugged into the equation for that.
If you could join me in thanking Amy Jo and her EPA colleagues. And I'm going to put just a couple people on the spot because we talked about testing. There is research going on right now. It's not ready and out the door yet, but if Tom Bridgman and Justin Chaffin could maybe stand up and wave your hand, they're working on some near real-time microcystin tests. So there are some technologies coming out to see if we can get those responses back from microcystin and other toxin loads. So again, Tom and Justin, just kind of wave your hand over here in the corner. So if you want to know about where that stuff, yes, thanks, Representative Sheehy. Just if you want to know where we're at as far as more rapid response for our recreational locations and things like that, that is definitely on the radar. So it's my pleasure to introduce our last speaker for the afternoon, Mandy Mickelson with ERDIC, as I mentioned earlier. So what we're talking about is the Engineering Research and Development Center with the Army Corps of Engineers. She's a research engineer with the U.S. Army Corps. She wins the award for traveling the furthest, so came in from Seattle, thank you, just to have this conference and dinner with Jay, because he's just lovely. And so I would please join me in welcoming Mandy. She's going to give us an update on kind of all the complementary synergistic work that's going on within the Army Corps related to what issues we're addressing in Ohio. So Mandy.
Okay. Well, good afternoon. Excited to be here. And I agree with Amy. Ohio is cool. That's one of my takeaways. This meeting is really great. It's awesome to be here representing our organization, the Corps. And I guess a take-home message from this presentation is the Corps was directed via congressional appropriation language and authorization that I'll share in a couple of slides here to deliver scalable HAB prevention, detection, and management technologies. And that's a tall order. And we can't do it alone. We really value the state of Ohio, all of our partners in Ohio, very, very much. I'll highlight some of the ongoing projects that we have going today, and we continue moving forward together in partnership. Let's see. Oop. Uh-oh. Green button? I'm sorry. It's this one? Oh, okay, cool, thanks. All right, awesome. So reported harmful algal bloom events are increasing across the nation. And so this is especially impactful to the Corps as we manage a vast quantity of water resource projects and across the nation that provide services like navigation, flood risk reduction, recreation, fish and wildlife management, as well as potable water supply. The image on the right-hand side here shows the nation divided up into districts. So the Corps has 45 districts across the nation. And those districts in various geographic locations provide technical support services to support a military mission, engineering services directly to military installations, and also support the Corps' civil works mission, which includes the services that I described earlier and involve operating our water resource development projects, et cetera. And so HABs significantly impact USACE for that reason, excuse me. And so like Chris mentioned earlier, I'm with the Technical Director's Office at the Engineer Research Development Center, which is headquartered out of Vicksburg, Mississippi. And we say one door to the Corps, meaning we all work together. ERDIC provides technical support to those districts, and we're working together in partnership with them to develop HAB solutions and to deliver this program. So sometimes I'll use USACE and sometimes I'll say ERDIC, and that's what I mean. That's the difference between those two terms. So the Corps has been involved in aquatic nuisance and invasive species research for over 100 years, for a really long time. But our specific focus in harmful algal bloom research ramped up in 2019 in response to the Water Resources Development Act of 2018, which tasked the Corps with delivering a 5-year HAB research and development program to deliver scalable HAB prevention, detection, and management solutions that would be applicable to freshwater bodies across the nation. In 2019, we first received funds to initiate that program, about $2 million, and then in fiscal year 2020, that number jumped to $10 million, and as a result of that initial investment, about 30 research projects are currently underway, and all are making great progress, and I'll highlight some of that here in the coming slides. The WRDA 2020, Section 128, authorized a new program, also called a Harmful Algal Bloom Demo Program, for short, which is intended to support technology transfer in a way to take those lab-proven technologies, move them into the field, and gather cost and performance data that will support end users understanding how to apply these technologies for optimal use at their field sites. I'll talk a little bit more about that program a little bit later. 2022 was a similar year in terms of appropriations, and we also received some funding to kick off that new field-focused demonstration program. Uh-oh. Okay, so now I'll give a kind of an overview, a broad brush of the activities that we have going on under these research focus areas. So a few examples. First, prevention. One example project, which is led by ERDIC researchers, involves characterizing and quantifying overwintering cyanobacteria cells that are present in sediment with the intent to treat, reduce their abundance, and reduce the likelihood of their seeding subsequent blooms. Another project involves use of gene silencing agents that has the potential to reduce the fitness of cyanobacteria growth and activity. In the detection focus area, examples include drone-based hyperspectral sensors and use of satellite sensors and development of algorithms to interpret that data to provide synoptic water quality indicators, early indication of harmful algal blooms in freshwater bodies. And another sensor, because as folks have mentioned, the importance of having quick information about presence of microcystin and their abundance in water samples, that's certainly been flagged as a need by water resource managers within the Corps too. So one example project that's currently underway involves a DNA aptamer-based sensor that will provide a approximate concentration and proportion to the signal produced by the sensor. And then within the management focus area, which is where a lot of our projects sit, there's multiple projects underway, including use of ultraviolet light is one example, and I'll share a little more detail about that one in the coming slides. Also looking at photo-reactive catalyst impregnated materials that can be deployed in water bodies and using either UV or sunlight to neutralize cyanobacteria cells, as well as cavitation, use of environmentally friendly flocculent materials that can sink cyanobacteria out of productive depths in the water column, and looking at ways to manipulate flotation of cyanobacteria to increase the efficiency of their collection. And then one project that was started in FY19, so it was an early start for this program. It's called the Harmful Algal Bloom Interception Transformation Treatment System. It's an ERDIC-led project. Dr. Martin Page is the PI, and there's been a lot of success with this project, or this technology, which uses, physically collects the cyanobacteria from the water, and then uses dissolved air flotation to separate the biomass from the water, and then uses ozone if needed, if microcystin is released into the water, to neutralize that prior to discharge, and then uses hydrothermal liquefaction to convert the concentrated biomass into fuel. I'll share a little bit more about that status of that project here in just a jiff. So like I mentioned before, we have multiple projects ongoing with Ohio Now, and many of the researchers are in the audience today. Nice to see you all in person. So the projects that are highlighted in green on this slide were initiated in early 2021 and are about at the midway point and are making great progress, starting to produce some publications, which is very exciting, so stay tuned. We're also excited to announce that we have 2 new projects that will be awarded this fall, later this calendar year, in the HAB prevention and HAB management focus areas. So excited to share that. I think contracting is still working, so, but good news. Uh-oh, excuse me. Okay, and then I included this slide, which is an excerpt of a conversation or a PowerPoint that facilitated a really cool conversation between the Corps and Western Lake Erie Basin Association partners. And the idea here, this diagram was just kind of illustrating a potential framework for us to sort of look together and think about how we could work together in this space. It was really great to listen to Ohio researchers and practitioners, experts, and learn about the data gaps and challenges and share about the Corps' research authorities and capabilities and kind of think about ways to most effectively work together. And those conversations were really productive. They, in part, resulted in one of the new starts that I shared on the previous slide, and also in another project, which is led by Dr. Ben Kokar, an ERDIC investigator, and also Dr. Jacob Berkowitz, also at ERDIC. And this is looking at bridging the gap between edge of field practices, receiving waters, and basically phosphorus sequestration in loadic systems or in the flowing waters. And so this project will begin later this calendar year. It's going to focus initially in FY22 on literature review and refinement of experimentation plans, et cetera. Then we'll focus on laboratory testing and optimization of the materials in the first year. And some of the example materials were touched on earlier by Dr. Penn, include inorganic materials, organic materials, and combinations of those materials, like rare earth elements and biochars and iron hydroxides in various combinations. So the first year will involve optimization of those materials for ultimate demonstration in the loadic systems, and then in FY23 and beyond, that's when the field demonstration components will be initiated. And this is really really an exciting opportunity for us to work together with partners. For example, OSU, Heidelberg University, and other universities, Defiance Watershed, H2 Ohio, Ohio EPA, Ohio DNR, USGS, and NRCS to leverage ongoing projects and work together to amplify the value of that investment and hopefully accelerate progress. Reduce the flash to bang, as one of my favorite program managers likes to say. Reduce the flash to bang time. So another example, now I'll talk about another couple of examples that are of particular interest to the region. This is another project led by ERDIC, Dr. Karina Young, and it involves use of microcystin degrading enzymes and deploying those to reduce the toxicity of microcystin in freshwater samples, or freshwater systems, rather. And so these are some preliminary results of a genetically modified bacteria containing the MLR-AB gene, and the results show a reduction in microcystin followed by a transient increase in the degradation intermediates of microcystin. So since that time, Dr. Young and her team have worked on production of the hyperproducing enzyme systems in E. coli, and has made progress, and the bottom plots here showing degradation of microcystin, and then in different treatments with cells containing the MLRA enzyme, MLRB enzyme, both A and B, some treatments, or the bicistronic MLRAB genes, And so at this point, the MLRA alone resulted in microcystin degradation and accumulation of the linear intermediate. But the combination of MLRA and B or the bicistronic treatment showed degradation and no accumulation. So it was another positive step. And so at this point, Dr. Young and her team are working on production of the enzymes and purification of them for ultimate demonstration, for ultimate performance testing. And so some example results for the MLRA enzyme are shown here, some gels identifying its presence in the samples, and similar to the results on the previous page, now looking at the enzyme activity only, degradation of microcystin and accumulation of the linear intermediate. And so next week, I believe, is when the remaining experiments for this will occur with the other enzymes. And so we're excited, really excited about this project, and should have new results to share later this fall. So another example includes the use of UV for neutralizing cyanobacteria cells and their toxins in freshwater samples, and this is led by ERDIC's Elizabeth Gao. And so last year, shout out to Todd Bridgman for providing samples, cyanobacteria containing water samples that were featured in the initial trials for this study, where Elizabeth and her team quantified the dose response, the dose and response, meaning the concentration and exposure time to the UV required to neutralize the cells. Here's showing some most probable number, looking at the viable cell counts as a response to different UV doses over time, as well as data not shown, the microcystin data is available as well. They've also done some looking at non-target organism toxicity of UV exposure. So that data is in hand as well. And so that report will be coming out later this fall also. So a lot of things in the works. Dr. Gao and her team will be in the field at Cullen Bay Park nearby in just a couple of weeks, so that's exciting. They'll be doing their field trials using the EGIT LIBOR vessel. That's something similar to what's shown here in the photo. There's a separate piece of equipment that's in production now. This is a CAD rendering of the vessel that Elizabeth's team is working on at this time. It won't be quite ready for field demonstration this fall, so we're going to use the EGIT LIBOR partner vessel. And some updates on the habitat system. Again, that started in FY19, mostly in the lab, doing benchtop work. In 2020, a lot of work went into optimization of the coagulant materials that are used in the treatment processes. And in 21, Dr. Page and his team successfully piloted the 100,000 gallon per day habitat system. And so that was done in Florida. And there's also a shipboard version of this system that was piloted that year in New York. So those results in FY21 were really promising. And so that progressed to this year, and this is kind of hot off the press. They just finished up in the field just a couple weeks ago in Florida, and they were able to pilot the 2 million gallon per day treatment system for habitats. They successfully ran it at 0.7 MGD, which was very exciting. Got some really nice preliminary results this year in Florida. And Dr. Page and his team will be supporting a nearby pilot project that's led by Wolpert and AECOM on Harsha Lake, and that'll be in a couple of weeks. And Dr. Page will be lending some field equipment to help out be a good partner. And also we'll be collecting some water depth-specific distribution data for cyanobacteria, which will be key for ultimately tech transfer and optimization of the habitat system going forward. So I mentioned this new program that was authorized that's all about field demonstration and gathering verifiable cost and performance data to guide end users' optimal use of these technologies. So again, that program kicked off this year. Want to say thanks to USGS and NOAA and US EPA for participating in the project selection process. We have 4 projects that are in environmental review now. We're hopeful that those projects will be officially selected and get started later this calendar year. And so if you'd like to learn more about that program, the link on the bottom of the screen provides a link to the USACE implementation guidance that has a lot of good information. So I've focused today on projects that are kind of ongoing in the region or of particular interest. And so we also have a lot of really cool work going on in Florida and elsewhere and across the nation. And so some projects in Florida are highlighted here, but I've also included a link to our website. I should probably make it bigger and bolder. It's there on the bottom right-hand side of the slide there, and that provides a link that gives an overview of the program. It has a table that features all of the current titles of all of the projects that are currently funded under this initiative and links to fact sheets and all kinds of good information there. So definitely check that out. And you know, I just feel really lucky to be here with you, to spend time with you today, to listen and learn, and to be a representative for this great program. I'm not the expert. I'm a program manager, right? But I'm happy to answer any questions that you might have now. And if you'd like to get connected with any of our researchers or want to know more, just feel free to send me an email. Thank you.
Thanks, Mandy. We have time for questions if you want to come up to the microphones. And one of the things, I knew this is what we were going to see, like all these great projects that are out there that we're going to get a snippet of. So I do encourage you to go to the website, but also reach out to Mandy because she's got a whole portfolio of things that are going on within the Corps that build off of what we're doing here in Ohio and build off some of the existing partnerships. It's been great to work with Mandy. So if anybody has any questions, please. And I'm looking online right now to see if we have any, so we'll pause here a second. All right, one last thing, Manny, if you can hang up here. I'm going to bring some of the other speakers up. We did have questions that came in that we didn't have the chance to answer fully. So, Angelica, do you mind coming up? There's a couple questions that came in for you through the chat that I want to make sure we get to. And as we get through these, then Jay will come up and kind of walk us out for the afternoon. So, Angelica, as you're coming up, the questions that came in was, and again, coming back to your dredge work, was any of the dredge analyzed for PFAs? And then also, was there any pharmaceutical work on some of those dredge materials that came up? I don't know if you know the answer to those questions.
I will ask, actually, Vanessa, do we have PFAS data? No. No, we have PAHs and we have, now I am forgetting. We don't have PFAS values, yeah. PCBs, yeah, I'm sorry. Yeah, and we also have some pesticides and, yeah, herbicides, but we don't have PFAS. Yeah.
Good. So if you're interested in any of the other analysis on that sediment, then if you could reach out to Angelica and she'll put you in touch with her team and get you some updates on that. And then I'm looking for, let's see, what else do we have here? For Kennedy and Haller, if one of you wants to come up and I'll read this as it goes. The question is, how much exposure can someone get from aerosolized toxins if they're out of the water? So not necessarily people on the water recreating, but maybe on the beach. So if you want to take a swing at that, please. So Dr. Kennedy's coming up.
Sure, thank you for the question. So the honest answer is we just don't know. and we need to do that work. So we know that different, congeners of microcystin aerosolize differently, so how they're represented in a bloom isn't exactly how they're in surface water isn't exactly the same composition as when they're aerosolized. We know that other aerosols can travel. Work from Andy Alt's lab has shown that these aerosols can travel some distances, multiple kilometers. But again, the detection methods and the actual real field work is still lagging, and we just to give a straight answer, we just need to do that research.
I think we're good. That's all the questions I'm seeing online. Thank you, Mandy. I will give you that. And I guess I'll just add 2 on the back end of that. So with the question that came to Kennedy and Haller, I do know that there's work, and I'm going to look at Tom as I say this. There's work coming out of UT, April Ames et al. And her colleagues that is looking at that aerosolized exposure. So they've got some monitoring devices on beaches, on vessels. So I know some of that work is still in play. And then we're aware of through, again, ODHE, HABRI projects, there is work going on in the foreshore sands. So if you're not familiar with that term, because I just learned it, when the waves wash up on the beach and then sink into the sand, but the sand is still wet, are the microcystins being accumulated in those foreshore sands, so that if you're digging sandcastles or playing in the sand, what's the possible risk of exposure through that route? So that work is going on right now, all projects that we hope to bring you through time. And so with that, I will pause and turn it over to Jay to kind of close us out for the afternoon, correct?
All right, my job is to give thanks to a lot of people that made this event possible. So first of all, thanks to all of you for coming here, and all of you who've been watching online. We did have good attendance, we feel like, first time out, hopefully in the waning stage of the pandemic, let's say. So thank you for coming, and have a safe trip home, or for those of you who are already at home, enjoy your afternoons there. I want to thank the speakers again. Let's give the speakers a big round of applause. And then I also want to thank the sponsors, who you can see up on the screen here. Very simply, this event would not happen without these sponsors, and many of them have been loyal to this event. I've been here for several years, and it's not just this event. These are groups that many of us researchers or policymakers work with as we explore the issues you learned about today, both in messaging, determining what the issues are, and also providing funding. So they're integral players, and thank you for the sponsorship today. Moving from there, I just want to thank a few individuals. So Shalise Simmons with OSU Extension, and Aaron Monaco from Sea Grant, really behind the scenes. Shalise greeted you as you came in today. Aaron couldn't be here in person, but both of them have been super involved in working with sponsors, getting you registered, and everything else that makes this conference successful. So thank you to Shalise and Aaron. I want to thank Joe with Vision Performance Group, who's been running the AV today. He's hidden behind this screen somewhere. Again, a long-term person who's supported this event, and his group is Vision Performance Group. So if you're looking for somebody to do AV for you, look for Vision Performance Group. Thanks to the caterer. That's Michael's Gourmet Catering. Did a great job with that. Hopefully you all enjoyed lunch. Shanahan Theater, Gabe and Ellie, thanks to them and the theater for hosting us again. I was informed that Ellie did try to reduce the AC and increase the temperature. I don't know if any of you felt that. There were some concerns about being too cold here, so we were trying to work on that as the afternoon went on. And then last shout out, I know he just left, but Tom Henry from Toledo Blade for coming here and covering this event, and hopefully you'll see an article on the Blade in future days. So thanks to all those people, and again, thanks to you for coming here and making this event possible. Please do fill out the surveys so we know what you're all thinking, and we can better plan for next year to have another successful event. Is there anything else I'm forgetting, Chris?
No, I just wanted to add my thanks again. It's so great to see academics, private industry, agencies, elected officials. I know Representative Sheehy was able to show up, and he's in the back of the room too. So again, this is many hands need to be working together on this. So again, I just love the diversity of this audience. So thank you very much, and everybody have a safe trip home.